people from geochemical models that you may have a non-plate tectonic setting on the early Earth. But the question is, we first time showed it in terms of the models, and again, to add a petrological connotation to it, we figured the best thing to explain the formation of the felsic crust at that time. And that is the formation of TTGs, the tonalite, transurban, and granodiorite gneisses. So in that, this is the same. There are two settings in the non-plate tectonic regime. One is the drips, as I was showing, and another was the thickening of the crustal domains. So you can see these pink dots. These pink dots are the residues that formed after the TTG extraction. So they are a kind of a marker showing where TTGs may have been formed. And this is within the drips. Here is the pink dots, and here is the crustal thickening. So these are the two sites where they can form. And when these markers are plotted here, this is the PT space again. The dots are these markers coming from here and here. And the fields are the domains of PT conditions that has been extracted from the natural TTG rocks. So these are the work or the data taken from Moe and Laurent in lithos. And when we plotted these markers, the PT conditions of these markers, the melting conditions of the basalts from the models, they fall pretty close on the what we observe from the nature. So this again brings the coherency that yes, the TTGs that are forming in this kind of settings can explain the chemical characteristics or the PT conditions of the natural rocks that we are finding in the field. So therefore, we have some sanctity in saying that yes, early to mid-Archean TTGs, which are the earlier TTGs, may have do not always need plate tectonics to form. They could have easily formed in terms of this kind of tectonic settings. So that was the basically thing to show how we can integrate this petrological and modeling stuff. So I think we should slowly and try to do this where we, of course, individually can do petrology, PT, kinetic modeling, and then zircon I just place as a symbol for geochemistry. Also geochemical tools. And you can integrate, and you can, if we can take the feedback from each of these processes, or the tools rather, then we have much better understanding of constraining the processes that are particularly occurring far behind in the time, because we do not have often access to the whole spectrum of the rock data. With that, thank you.
Thank you, Yogesh. Thank you also for finishing on time and your time for questions.
You can just speak, I'm fine.
So we have applied the diffusion chronometry techniques.
Can you use the microphone, please? Hello.
We have used the diffusion chronometry in tonalite facies rocks. So
yeah.
Out of curiosity, I want to know, is it possible to apply the same technique in the blue schist and eclogite facies rocks?
Yeah, I mean, it depends on the mineral system that you're using and the elements, and whether the diffusion exchange happened above the closure temperature of in that domain or not. But I think eclogite you can definitely do because high pressure, high temperature. Blue schist I'm not experienced, but if you can get a certain right pair of the elements and minerals within that temperature range, I think you can get it.
Thank you. There's two more questions over there.
Excellent talk. You talked about crustal delamination in your model. So for that, I wish to know that did you use a specific rheology and that led to that particular delamination? And how do you pinpoint that rheology for the delamination?
Yeah, so no, we used this, again, parametric study. We used various rheologies that are available. So we use weaker rheology, for example, that are proxied by quartz, wet quartzite model. And we also use some dry or more stiff rheologies in terms of dry granulite or felsic. These are different models I'm saying. But we use over a spectrum. The problem is we got delamination in most of them, except one which is extremely dry diabase they are called, which is extremely, extremely stiff. And I don't think that's very realistic. But the problem is here, delamination is happening, of course, there is a rheological control, no doubt. But all the rheological models are dependent on the temperature. Because your mantle is coming up, you are bringing so much high temperature at a shallow level, you are automatically creating melting. Now, once you start melting, that melts is now facilitating the delamination. So instead of the dry rocks, the rheology of the melts and the melting temperature also becomes very critical.
So as an addendum, you talked about mantle coming up. So is the delamination plume driven or is there a scope of edge-driven convection?
Yeah, you don't need plume in this setup at all. I mean, I'm not saying plume cannot drive that, but for here we do not have any plume settings. It's completely driven by the slab movement, so you can consider them as an edge movement. But the plume, the mantle upwelling is coming up because the slab is actually falling faster, and that's because the mantle is so hot, it cannot provide enough resistance to the flow of the lithosphere inside it.
Thank you.
There's another question over there at the back, and then I'll come to you, sir.
Priyadarshi, this is
Yes,
a
sir.
question perhaps not directly related to what you have talked about today. I am curious to know, one of the fundamental conditions for the operation of plate tectonics is that the crust must be divided into plates, segmented into plates, instead of being a continuous crust. So in your model, how do you account for the segmentation of the crust into different plates?
So in the first case, because we are studying the nature of the plate the orogenic process, we initially imposed a boundary, the plate tectonic boundary, which was imposed with the help of a weak layer, and we are enforcing it. In the second case of models, which I show a spontaneous transition from drips to that, so we are not, because the 2D model, we have a restriction that we cannot have a 3D distribution of the plates, but what we can see is that because drips are also creating lithospheric discontinuities, and so that is then facilitating.
Use the microphone. Get the microphone. Because it's important for everyone to follow the discussion. Yes, sir. Behind you. Yeah.
So fundamentally, is it, are you suggesting that it is the operation of the drips at different locales which is giving rise to the segmentation of the crust into different plates?
That was one of the implied inferences from that paper, because one of the major thing is how you can create discontinuities in an otherwise homogeneous lithosphere. And you can have damage systems given by Berkovici and all those people. But even in the damage, you need to create the damage first. And how would you create that? So one of the ways is that because deformation was happening even without plate tectonics, that was intralithospheric, may not be of the same magnitude as we see today. The nature was different, more distributed strain perhaps, but still you have you can create lithospheric discontinuities. And the question is now whether that can act as a seed for the failure of the lithosphere. Now from the model perspective, they are showing it is, but still it is a very nascent stage, and to figure out whether that happened or not, we need to go to the field again. But I don't know what is the appropriate rock type because most of the mafic rocks are gone. So that's a challenge there.
There was some question at the back, maybe? Was it? No? If not, yeah, something.
Priyadarshi, nice talk.
Thank you.
I have such a very small query, that is, you are showing that you are applying viscoplastic rheology in your model. And you are showing there is a delamination between the lower crust and the upper crust and sort of things. So where exactly, what kind of bulk rheology, is it a rheological equation applied to the whole bulk of the crust, both the upper and lower, or what you are suggesting?
So we are using different flow laws for individual crustal layers, upper crust, lower crust. For example, upper crust we use, and both diffusion dislocation creep and Drucker-Prager criterion has been applied. The idea is that whatever the limiting strain rate would be, that will determine the viscosity.
In viscoplastic, how do you apply Drucker-Prager? Drucker-Prager
So
will be in a more
so we use it as limiting agent, so it's such that it should not go above the brittle failure.
Okay. And the lower crust, you think it is behaving in a Kelvin type material, or it's a elastic, partly elastic, like say Maxwell material?
So in these models we cannot use elastic because the codes are not that way to handle it at that temperature.
But nowadays we think
we can. So we can.
Because earthquakes occur at base.
Yes. So one thing is also I would say, because these models are, and I think from a modeling perspective, these models are not suitable for studying earthquakes because they are not designed for that.
Yes.
If you want to do that, then of course you need to have elastoviscoplastic or elastoviscous models, that kind of thing. So therefore, the only thing that you need to change is how you apply the rheological flow laws, or the constitutive equations. Yeah.
Anthony, yeah.
Thanks, Priyadarshi, it's an excellent talk. So you talked about the big tectonics regarding early type of, not the horizontal tectonics and that, right?
Yeah.
That's the start of this. So to talk about that, so you said there's a cooling of the mantle with drift. Right? So could you quantify that? What rate the mantle?
Oh yes, we can. I don't know whether it's there or not. So that's exactly what we did. But I don't know whether exactly that slide I have it here or not. So one way of it's not a quantification directly, but you can show what is happening at a one snapshot. So if you look at, so what we're looking here at the formation of the rigid, lithosphere. So this is again the drip stage, one snapshot of it. And this is the subduction stage, one snap of it at one time. So what we're looking at is that how horizontal velocity of the lithosphere is. This is the proxy for how the strain is accumulated. Here you can see the formation of plate, as in you do not have internally strained condition that much, so you are transmitting it, so which is corresponding to the lateral motion of the plates, whereas in this case you do not have. But the heat is the heat flux. And at a one snapshot, we can see that how the heat is coming up or going down. So we actually calculate it over time, like the average heat loss from the mantle, and we could actually show that the mantle heat is declining, say in terms of potential temperature.
Okay. So did you try this with the three-dimensional model? No?
We will, but that will require a lot of computational things. So that is the problem right now here. But in terms of simplified models, yes, you can. But these have a lot of petrological calculations also, and that takes a bulk of a huge amount of time. So in 3D, I'm saying. So yeah.
Thank you. Thank you.
Thank you.
If there are no questions, I have one pure question. So if you go back to the DTG generation thing, this is something that came up yesterday in a discussion, so I want to hear your view on that. Yeah, so one of the things is you're melting, making the DTG at quite high depths at 15 to 20.
It's 15 kilobar, roughly.
15 kilowatts. And what you also know from petrology is you need hydrosmelting to do that. So how do you get the water in that depth without the tectonics?
So in that case, one thing is, of course, the drip. So previously we thought how the water would come, and now we can clearly see the water can be transported through drips even from the surface. But of course, whether to 1.5 or not, that's a question, because we do not have direct evidence for that. But recently paper came out, not recently, last couple of years, that they could figure out the oxygen isotope from zircons, I think by Hugh Smith and all. And they found there was some mantle signature on the water conditions. So delta 18 oxygen value is very close to 5.5. So if that is significant part, I'm not saying it is, but if it is, then you can also have water coming out somewhere from the deeper sources. And you always do not need surface water to go down. But that's a separate discussion. You can still have water coming in through drips. The problem is having water here at the base of the thickened crust. That we are not sure how we can have water. So if the mantle water may have played a critical role, that would solve this conundrum here. But for the drips, you can easily have water coming on, because these are basically greenstone facies rocks, the greenstone belts, so it can bring down water. So it's not a big problem.
If it can take water. The reason I bring it up was because there was a talk yesterday on Bundelkhand gneiss, and there are apparently some indications that you can have deep water quartz veins in there. So that would be a good tea time discussion. So with that, I will let you get started on the tea time break, because I don't want to cut into that. But that's something we can discuss on the break. Thank you, everybody, and convene in 10 minutes.
Thank you.
reflected star. It is just hanging. That's a no. That's what I'm saying.
That's a $1 billion question.
Hello, check, hello, 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 check, check, hello, hello, check, check, hello, hello, check, check, hello, hello, check, check 1 2, hello, check, hello, hello, check, hello, 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 check.
চট করে
আমায় বলছো? আমি না, তোমার ওখান থেকে দেখো, ওনাকে জিজ্ঞেস করো। ঠিক আছে? এই দাদা, এই লাইটটা ঠিক আছে কিনা জিজ্ঞেস করছো, দেখো তো পোডিয়াম লাইটটা, মানে তোমার ক্যামেরা কালছে আছে। হ্যাঁ, ওনাকে বলো, ওনাকে বলো পোডিয়াম হালকা এবার ঠিক আছে। পোডিয়ামটা কেটে পিছোতে বলছে। হ্যাঁ দিদি, তোমার কিছু সময় হয়েছে। अभी रमन सर का स्टार्ट होगा।
मैं आज में क्या हुआ गलत बोला उतर गई
कहाँ?
एमजी रोड में मतलब
है ना, वो गलत नहीं है, मैं तो एमजी रोड से आता हूँ,
मुझे मतलब मुझे इस समय आना पसंद नहीं है।
सेंट्रल वाला कोलकाता पसंद है।
इसमें थोड़ा कम लोग हैं एमजी रोड डर्टी होती है
एक्चुअली
एमजी देखते ना अच्छा नहीं लगता है।
इवन मॉर्ग भी है तो मतलब मेन रोड में नहीं है, पीछे वाला रोड मैं नहीं यूज़ करता, मॉर्ग वगैरह बहुत कचरा है, लेकिन मेरा लड़कों को भी सर्च हमेशा घूटता है, इसलिए मैं इन जनरल हेडफोन लगा कर मैं निकल जाता हूँ। পোডিয়ামটা বন্ধ করবে? দাদা পোডিয়াম মাইকটা একটু অফ করো না।
কেউ ঢুকবে কিনা সেটা কখন হয়েছে চায়ের বেশি পারিমাণিক ছিল
আগের দিন ছিল
না আমি তো দোকান ছিলাম আমি করে বসেছি পিছনের দিকে কিছু করে
দেখলাম আজকে আর দুটো ডাইরেক্ট
আমি তাই ভেবেছিলাম বাড়ি ঠিক আছে চলেই যাই সত্যি 1 ঘন্টা করে লেগে যাবে
আমি তো কেষ্ট বলে থাকছি
কেষ্ট পয়সা কাটিস সরষে কাটিস
কিন্তু ওখানে খানিকটা খুব ভালো করোনা থেকে
মেট্রোটা চালু হয়ে গেছে
45 মিনিট
একদম
নো চেঞ্জ
পাক দিচ্ছে শুনলে তো টক
না না আমি
অনেক বছর আগে প্রথম যখন নিজেদের কাজ করা দিচ্ছিলাম এখন তুমি তো তারপরে আবার অন্য ডিভিশনে মুভ করে
এখন তো অনলাইনে আছি আর এখন ট্রেনিং স্টুডেন্ট ট্রেনিং করে আমি আসি সল লেগে মেনটা হায়দ্রাবাদে আমাদের এখান থেকে আমরা তারই একটা পার্ট রিজিওনাল পার্ট তার একটা
ধরে রেখেছো
ধরে রাখা তো সম্ভব না কারণ আমার কোনো অ্যাক্সেসটা নেই পুরোনো কাজ নেই
এখন
প্রস্তুতিও নেই না মাথায় ছিলেন আমার দুটি মেয়ে আছে শৈবালকে ধরতে হবে শৈবালকে আকারে মানে তার বস শৈবাল তাকে এলিমিনেশন করবে ওই আইনটা ইয়ে করে কালকে এসেছিলেন
পৃথিবীতে টক দিতে গেছিল
ছিল
ছিল ঘোষ পৃথিবীতে টক দিয়ে
গেছেন এখন তো কাজ করতে পারছেন এখন তো এসে চলে গেছে ওই ব্যাপারটা ওনাদেরকে করছে তারপর উনি
চায়ের থেকে লোকেরা কখন ঢুকবে সেটা রাখা হবে
শখ নিয়ে আছে শখ কি আছে ইউএসএতে কত একটা ল্যাব অন্য ল্যাব My wife always talks to the wife is 25 more
much more water.
আমরা যদি একটা ল্যাব থেকে অন্য ল্যাবে শিফট করি তাহলে মোটামুটি এখন 10 বছর তো হয়ে যাবে এখন যা পলিসি আছে হাইয়েন্ড ইকুইপমেন্ট কেনা মোটামুটি 2-3 বছরে ইকুইপমেন্টের প্রশ্ন হয় কিছু হয়ে গেছে এভরিথিং ইজ ডান আওয়ার লেভেল আওয়ার 2 crore স্যাংশন somebody from the ministry and what industry and to very close to that उससे क्या होगा so we'll get that उससे क्या होगा उससे क्या होगा उससे कुछ नहीं everything is done for last almost more than 1 year
হ্যাঁ
সিস্টেমে কাটতে জানা
অনেক টাকা মানে আমি জয়েন করেছি সেটি গিয়েছে একটা ছেলে আমাদেরকে ভিজিট করলো বললো কি আমরা 2 CR মতন পেয়েছি হ্যাঁ আমি কিছু হাই প্রেশার ডিভাইস কোন ডিভাইসে কাজ করেছি আগে কোনো ডিভাইস দেখিয়ে ডাউনটা তুমি চালাতে
ডাউনটা তো ডাউন হয়ে গেছে ডাউনটা বয়স হয়ে গেছে তারপরে 10 বছর হয়ে গেছে
আসলে সরাসরি আগে দিনে আসি কারণ আমরা রেজাল্টটা আমরা গ্রিফ লাইফটি লাগিয়ে চালাচ্ছি আরও ছিল তো ছিল যখন পার্টটা শেষ করতাম সফটওয়্যার পার্টটাও আমরা হ্যান্ড করে যাচ্ছি স্যাম্পল আমরা রেজাল্টটা এক জায়গায় দিনটা করছে হয় এখন ওই সময়টা ভালো চলছিল কনফিডেন্স সেটা some theory behind it because giving you the correlation. Difficult to constrain. Manipulation, কাকে কাকে কাজ করবো স্টেট একরকম কন্ট্রাক্টে একরকম বিশাল হয়ে যায় কী করতে পারো সেটাই শিফট কম্পিটিশন ঠিক আছে fundamentally using it nice to খেলাম শেষ করে তারপরেও constantly going on. Last year to the field access to mushkil hai because one is publish kar rahe hain very good project one department to another department permission তাও মানে
তাও তো আমার মনে হয় আমি তোমাকে তুমি একটু টেম্পারেচার একটু বাড়ানো যেতে পারে একটু অস্বস্তি হচ্ছে যেন মানে কমফোর্টেবল জায়গা দিয়ে আনকমফোর্টেবল একটু বলবে টেম্পারেচারটা কমিয়ে গরম করতে কমিয়ে মানে সরি মানে আমি বলছি গরম করতে রাইট তাও তোমাদের তো অনেক আমাদের সাথে কম্পেয়ার করে কোনো লাভ নেই আমাদের এখানে আমার ডিউ স্পিক
আমার কাছে কিন্তু শেষ করে আমার আমি 18,000
ও একদম এখানটায় আমি তো আগে এই সায়ন্তন আমি করতে পারবো তোমার ক্লাস তোমার
আপনি
বলতে শুরু করে লোক ঢুকে ক্যালকাটায় ছিল
চায়ের পরে আপনি মানে তোমার সাথে আমার আমার পরিচয় নাম তো সবসময় এখন আমার কিন্তু আরো ফাইল মানে
বাবার সাথে আমার পরিচয় ছিল গল্প পিরিয়ড আমার সাথে অনেক সময় মনে হচ্ছে কেমন আছে
তুমি আর কাজিন না দেওয়াঞ্জন পারতেই গেছে আমার মনে হয় আমার ছেলেকে দেখেছি ছেলে গেছিল সবাই
Hello?
না
Please, let's get started. Would you please come back and take your seats because we don't want to delay our lunch as well here.
একবার নেবে চলে যাবে
So welcome, please welcome. You're welcome to the second half of the session, and we start with Ramananda Chakraborty on tracing mantle heterogeneity using novel isotopic tracers. Ramananda, please.
Yeah. Okay. Thank you, Professor Chakraborty. Okay, so it's an honor and a pleasure to be back, to one's alma mater, and of course, many moons ago, this was a place where we would mostly visit when the Milieu, fest was actually going on. So it's a very different thing, and it's indeed an honor to be part of a meeting honoring Professor Shaha, because although we were not direct students, we were actually in the first year when we would see him come to the department occasionally, but unfortunately that was not too long ago before his untimely death. But it's a pleasure. So thank you to the organizers, Professor Bose and Professor Ghosh. So the work I'm going to be presenting today is essentially a combination of contributions from several students, past, some present, and this diagram basically tells us, the motivation behind what I do in my lab, and that is to study mantle heterogeneity. And of course, the schematic representation is basically telling us that it's primarily crustal recycling that results in mantle heterogeneity. And what we are trying to address in several problems are what are the recycled materials? I mean, can we distinguish their relative contributions to mantle heterogeneity? The age of the recycled material. That, of course, we've heard talks about initiation of plate tectonics or similar processes. How far back in time can we actually trace these recycling signatures? And then finally, what kind of tracers do we use to track these? Now, of course, we are not the first to target this kind of a problem. And if you go back, if you have a student audience out here, early 80s, people were actually analyzing, oceanic basalts to come up with these large heterogeneities that are visible, and about 2.5 decades later, this was actually termed as the mantle zoo, where we have data from oceanic basalts that basically tell us that we need different so-called end members. But one has to remember that these oceanic basalts are only about 200 million years old, so people working with samples do have an issue, and so we would like to track the heterogeneity even further back in time. And in today's talk, I'm going to tell you a little bit about these unique igneous rocks called carbonatites, which, of course, there are experts out here. They have modal carbonate minerals. And even for carbonatites, this recent review paper by Greg Yaxley kind of shows us that there's a large bit of heterogeneity even within carbonatites when you consider the traditional radiogenic isotopes. So we would like to kind of target the same problem, but in this case we are using slightly different tracers. I wouldn't call them novel, so I've kept it within quotes, but they are relatively new. And because carbonatites are mostly carbonate mineral, bearing material. So we thought, why not target tracers that can track carbonates? And so that's bringing us to calcium stable isotopes. So we have 6 stable isotopes of calcium from mass 40 all the way to 48. And because we have a relative mass distribution of about 20%, it kind of makes it likely to undergo mass-dependent stable isotope fractionation. And what we do is we kind of do a double spiking and a thermal ionization mass spectrometry technique to measure these isotope ratios. And what I'm going to do is report the data using the standard delta notation, which is basically with respect to a standard, and the deviation is used in parts per 1,000. Another reason to actually use calcium isotopes is because when you look at the general variability of calcium stable isotopes in natural systems, silicate rocks have a range, but then carbonate rocks have an even wider range, and many of these values are lower than the so-called bulk silicate earth value. And so that might be a useful way of tracking carbonates in the mantle. So we not only did some field work to collect our own samples in India, but we got samples from all over the world, carbonatites of different eruption ages. And the diagram on the bottom basically shows you delta 44 calcium values of carbonatites versus their eruption ages. And this horizontal gray bar is essentially the estimated value of the mantle, the bulk silicate earth. And if you, for the time being, ignore the southern Indian carbonatites out here in the Phalaborwa in South Africa, you'll see that most of these slightly older carbonatites, which are older than 300 million years or so, have mantle-like compositions. But then the ones with eruption ages less than 300 million years actually have large variations, and most of them are showing lower values, which is suggestive of increased crustal carbonate recycling in the mantle. And the upper diagram essentially zooms in. So you can see that these blues and reds are either whole rock carbonatites or calcite separates. So they are all showing this kind of a recycling signature. Combined with calcium isotopes, we measured radiogenic strontium isotopes on the bottom right on the same exact samples. And again, if you ignore the southern Indian carbonatites and Phalaborwa, you actually see that most of these older carbonatites lie on the so-called mantle evolution lines. And then once you come to the younger values, they have more radiogenic values, suggesting increased crustal signatures. So the next question was, what is the age of the recycled component that's actually causing this heterogeneity? By then, there's a lot of data that was available for calcium stable isotopes for Phanerozoic carbonates and Precambrian carbonates. And if you look at the Phanerozoic carbonate panel on the left, you'll find that the gray bar is again your mantle, and there's a lot of carbonates that are showing lower values. But the interesting thing is when you go to the Precambrian, compared to the bulk silicate earth value, you actually see overlapping values for carbonates. So the similar data sets are also available for radiogenic strontium, work by Jan Weiser and others. And if you combine all this information and you look at a delta 44 calcium versus a radiogenic strontium plot, for the younger carbonatites in the study, we basically find that we can find up to 28% contribution of Phanerozoic crustal carbonates in the mantle source of these rocks. So we could actually get an age constraint, and some of these carbonates could be between 100 to 200 million years, and some between 400 and 500 million years old. But then, of course, nature will not follow exactly the simple models that we try to create. And if you look at these filled circles, the black filled circles, these are all carbonatites from a single province. There's the Ambadonga region associated with the Deccan plume. And you have large variation within a single province. And that we basically investigated in a different study. We looked at not only the filled circles, which are the carbonatites, but the associated other silicate rocks. And we basically argued that we need some kind of an end member. So your mantle is up here, and your end member, the crustal end member, must have a 87, 86 value of between 706 and 707. And that kind of corresponds to about 1 billion year old crustal carbonates. This is from the marine seawater evolution diagram. I like to use the older ones. We also measure neodymium isotopic composition in the same samples. And again, if you look at this trend line, so to speak, you need an end member which is about -0.5 to about -8. And again, it turns out for the neodymium isotope curve for seawater, it's a similar 1,000 million year carbonates. So we think that the Ambadonga is basically, of course, this is all part of the Deccan plume, but these are ancient subducted material that are entrained within these plumes. There's also another interesting relationship for the Ambadonga, and that is if you plot delta 44 with respect to the potassium-rubidium ratio, and of course, between phlogopite-rich and sources and amphibole-rich sources, the K by R rubidium ratio actually changes. So the green is amphibole out here, and this is phlogopite. You can see that the carbonatites are more on the phlogopite-rich end member, while the other silicate rocks are on the amphibole-rich end member out here. Now, the presence of phlogopite versus amphibole also has some depth implications in the mantle. And so phlogopite, of course, again, with this yellow bar, is stable at slightly greater depths, maybe up to 150 kilometers. But if you have fluorine-rich phlogopites, they can be stable at even slightly greater depths. And the presence of fluorine has implications for Ambadongar, because we have these large fluoride deposits associated with these carbonatites out here. And so we argued that maybe they're all coming from the same plume, but the silicate rocks are coming from a slightly shallower source in the plume, and the carbonatites are from a slightly deeper source. But then when we go back to the global carbonatites, there was a bit of a problem. And that is, this is an older paper that was on boron isotopes in carbonatites. And again, they argued that the younger ones basically have this crustal recycling signature. So we wrote to the authors of this paper, Tony Semenith, and said, can you give us the exact same samples, and we would like to measure calcium. So the blue data is your calcium, kind of a similar trend, but if you plot sample to sample, you find no correlations. And that means that these boron and calcium, and so they're also all being recycled back into the mantle, but different phases are possibly carrying them. To investigate these phase dependence, we kind of said, let's look at some other new tracers. And so that's where we not only, so I told you about rubidium, decay of rubidium-87 to strontium-87, which is your radiogenic strontium isotope, but we wanted to investigate the stable strontium, that is a ratio of 88 over 86. And again, we measured this in our lab using a double spike thermalization mass spectrometry technique. And there's some data that is now currently available for delta 88 values. You can see that these are peridiotites up here. The gray vertical bar is your estimate for the bulk silicate earth. Carbonates are again showing lower values. And we go back to the same set of samples on which we had measured calcium, and a selected subset of those samples were measured for radiogenic strontium again. Again, you have the similar trend. Ignore the Southern Indian and the Palaborva for the time being, from mantle-like values to more crustal-like values. But then, when you measure their delta 88, this is what we see. So this horizontal bar is your bulk silicate earth estimate. And we basically find that most samples are overlapping with the bulk silicate earth. There are some that are showing slightly higher values, but if you zoom into those samples, you actually find that they're all from Ambadongar. So barring the Ambadongar carbonatites, which actually have slightly higher delta 88, every other sample from all over the world that we have measured are all showing bulk silicate earth values, which is puzzling. Let's focus on the Ambadongar. So if this is your mantle, the shaded bar, you have Ambadongars that are slightly higher. The fluor spars from Ambadongar are sitting up here. So extremely high values, both in terms of delta 88. Even for calcium, they had very high values. And we believe that the Ambadongar, this is kind of a syn-eruptive maybe process, or maybe post-eruptive related to hydrothermal alteration. And so that's exactly what's causing the stable strontium isotope fractionation. But when you look at the global samples, there's no trend with calcium oxide or lanthanum by ytterbium. So there's no real effect by partial melting. So we started wondering, why are the delta 88 values of global carbonatites invariant, and does it have any implications in terms of what is being recycled back into the mantle? So when we look at the recycled lithosphere, we can look at ophiolites, and if you look at ophiolites, you basically see these ultramafic layers, the mafic crust out here, and of course you have the carbonates and the hemipelagic sediments, and there are thickness estimates of of these individual lithologies in the entire lithosphere. And so if you now consider the end member composition, so this is 87, 86 on the right-hand side, and you have carbonates out here, you have peridiotites, and you have basalts. On the left side, you have some end member values for carbonates, again, maybe some basalts and peridiotites, including the altered oceanic crust. You can actually start doing some mass balance. And you can say that, well, the entire lithosphere, we consider these three different components with different strontium concentrations, 87, 86, and delta 88. And this is what we get. This is a 3-isotope plot for strontium, where we are now plotting delta values on the y-axis, radiogenic strontium on the x-axis. This is the range of values for peridiotites. This is the green star is your morb, and this is your carbonates. And this calculated mixed package basically shows you a composition that actually overlaps with the bulk silicate earth. So the fact that it does not show a signature beyond, that is different from the bulk silicated does not mean there is no recycling going on. This is the curious case of having a false negative signal. And this is a term that I guess during the COVID era had become very popular, or unpopular rather. And so anyway, so the point is the lack of a signal does not mean that you don't have the processes that are going on. We've been investigating this a little bit more, and so we've now started working on the samyelophyolite. These are, from Matthew, at UC Santa Barbara, and we can find that there are some mineralogical constraints which might be causing maybe some low delta 88 strontium. We've also been working on samples from the Hess Deep Rift, and where also there is evidence for seawater alteration. And again, on a delta 88 strontium versus delta 44 calcium, we do find large ranges, but I think a lot of this is related to mineralogy of these samples. So with that, I'm going to just stop and leave you with some take-home messages. Indeed, when you look at these slightly more newer tracers, you're able to put some age constraints on what is actually being recycled back. So in some cases, there could be 100 million-year-old carbonates. In some cases, maybe 1 billion-year-old carbonates. We can also get some depth constraints when it comes to the origin of some of these igneous rocks or the melts. And the fact that we did not find any variation in delta 88 values does not mean that there is no recycling. It just means that this is not an ideal tracer to basically track recycling back into the Earth's mantle. So I think I'll stop there, and I'd be happy to take some questions. Thank you.
Thank you, Ramananda, and again, thank you for staying on time. Other questions? See any hands? Anywhere, everybody? Usually I'm used to that. Is there somebody? No, because I'm used to seeing when people talk about mantle heterogeneity, a lot of questions. Is somebody back here? Yeah.
Thank you, sir. I'm Shomadip Bose from Jadavpur University, and you showed the recycling of calcium. Is there any correlation between calcium and carbon? And have you checked the carbon isotopic values for those carbonates?
Yeah, so most of these carbonatites, so the first thing is you screen for delta 18O for alteration, and then also for, these are all mantle-like. So the thing is, the carbon is all mantle-like. And, but the calcium isotopes are actually, we're trying to track the carbonate, okay, but a lot of the carbon is actually mantle-like.
Okay, thank you, sir.
Any other questions? So do you have some sense of what the ideal tracer would be?
Well, I think the take-home message was also that I think with improvements in mass spectrometry, we tend to measure a lot of newer things. But I think it's the puzzle is there are, if you look at these tracers individually, they all show you some signs of recycling. But I think it's still a puzzle as to why when you look at the radiogenic isotopes, we all know that there's a negative correlation between neodymium and strontium because it's a good tracer of sources. But with these metal stable isotopes, they can be affected by sources as well as processes. And so that's basically, it's an advantage, but it can be a disadvantage at some level because you don't get these correlated variations. And so I think, the approach should be to find multi-proxies so that you can nail down that is this recycling because of recycling of hemipelagic sediments, or is it because of an altered oceanic crust? If you go back to the standard mantle zoo, your EM1 and your EM2, we've always said that, it's subducted material that has high uranium, lead, and hence high mu. But what exactly is the carrier phase? When we say enriched mantle, of course, today with Matt Jackson's paper, we even have found traces of continental crustal material that has been recycled back. So that is one end member. But then I think this is where what we're trying to address is there are certain tracers that might be able to track carbonates, certain tracers might be able to track clays. We started off strontium because we have a lot of data where we find that during crustal weathering, these get fractionated. And so if that's the material that's going down, so there are some unpublished literature also for hemipelagic clays where they find variations. But when you look at the entire package that goes down, it seems like the mass balance is canceling some of these signals out. So yeah, the search is on.
So these isotopes are pushing you to more understanding the process, which I think is
That's
good.
right. Yeah, yeah.
If there are no questions, thank you, Ramananda, and we'll move
Thank
on
you.
to the next.
Thanks.
So our next speaker is Professor Sujoy Ghosh from IIT Kharagpur. So it's my pleasure to welcome Sujoy Ghosh onto the stage. His talk, the title of the talk would be Formation of High Pressure Phases in Shocked Chondrites.
Prefer this pointer, this for change and this for pointing the upward, or this one on screen one. Then you don't have to look backward.
Okay, so I'll use this one.
Will you find?
And I have to use this one here.
This one, or this one will do.
This one, okay, thank you.
Okay, so sure.
Okay, thank you for this invitation, and it's great pleasure and honor to be part of this conference, which is in honor of Professor Saha. So in this presentation, I will be talking about some of our recent results on Indian meteorites, and we will try to understand the formation mechanism of these high pressure phases which are formed in these shock meteorites, and how we can imply all this formation mechanism to the this application. So if we talk about the oxygen fugacity, so oxygen fugacity is the chemical potential of oxygen, and basically it is synonym to your mental redox. So if we try to see the variation of oxygen fugacity in terrestrial magma, so this x-axis is basically oxygen fugacity relative to nickel-nickel oxide buffer. So we use different type of buffer, and so we have this FMQ buffer somewhere here, and then we have a iron wüstite buffer which is more reduced, and then we have a magnetite hematite buffer which is more oxidized. So if we see this histogram, so what we notice that when we have a morph, it's relatively very reduced, not very reduced, but it's reduced compared to the Hawaiian basalt, which is relatively close to the FMQ buffer. Then we have this arc magma, which is oxidized, and then we have a very oxidized magma, some alkaline magma. So if we see the order of magnitude change in the oxygen fugacity in the terrestrial magma, so it's close to 8 order of magnitude. So the next question is, when we go deeper, so how the oxygen fugacity changes with depth. So this is a very nice diagram, and in this diagram, actually in the y-axis you will see the log FO2 relative to FMQ buffer, and in the x-axis we have a pressure which is equivalent to the depth, and all these points are basically calculated oxygen fugacity of mantle derived this xenolith from different cratons. So all these colors are basically mantle xenolith from different cratons. So we have a slave, we have a kapwal, and so forth. So if you will carefully see this diagram, what you will notice that if we take a sample at 2 GPa, so the fugacity is very close to the FMQ buffer. But when we go deeper, let's say at 6 GPa or 7 GPa, which is equivalent to your 200 kilometer depth, the fugacity is almost like 4 order of magnitude lower than the FMQ buffer. And why we have this trend when we go deeper, this is mainly because we have this Fe2O3, this component is going inside the garnet structure. And when the Fe2O3 is going in the garnet structure, because garnet is more stable when you go deeper and deeper, so basically this is basically decreasing the activity of Fe2O3 in the rock, and then they are basically reducing the oxygen fugacity. So when we go deeper, we basically reducing the environment. So many people are interested to know the fugacity condition in the transition zone and in the lower mantle, and we know that we have very less number of samples from the transition zone and from the lower mantle. So this is a very important concept introduced by Dan Frost in 2004, that is a disproportion of iron, this concept. So basically what he did, he basically took instantite this sample and synthetic sample, and he mixed with some metal powder and compress it at a very high pressure up to the lower mantle pressure, and heat it at a mantle adiabatic temperature, and then he tried to see that what would be the proportion of Fe3 plus in the bridgemanite, which is a lower mantle phase. So those who are not aware of bridgemanite is a lower mantle phase which has a perovskite structure, and 75% of the lower mantle is made up of bridgemanite. So when he analyzed his sample using the ELS technique, so what he noticed that his sample contains a very high amount of Fe3 plus, and this ratio of Fe3 plus divided by total iron is varying from 0.4 to 0.7. So when he has a lower amount of aluminum, so he has a lower this Fe3 plus by total iron, but when he has a more aluminum in the system, so he has a higher this proportion of this ratio. So he came up with this idea that if in the bridgemanite, which is a lower mantle phase, if you're adding loss of this Fe2O3, that is a Fe3 plus, so if you are forming a Fe3 rich this bridgemanite in the lower mantle, so they will always coexist with this free metal, and this will happen by the disproportion of iron. So basically in his sample, what he noticed that some free iron was present that is coexisting with a bridgemanite. The similar kind of set of experiment people have did in the much lower pressure. So there is another interesting phase, that is a meteorite. Meteorite is a variety type of you can say garnet, in which you have a silica coordination is 4-fold coordination as well as 6-fold coordination, and this mineral is very silica rich, so you have more than 3 atom per formula unit of silicon in majority garnet. So the similar type of experiment people did, and what they noticed that they are getting a similar kind of this iron disproportion of iron of this majority garnet when they coexist with a free metal, and their ratio is Fe3 plus by total is close to more than 0.3. So from this, Dan Frost and Catherine McCammon, they basically calculated the oxygen fugacity variation with depth, and this red line is basically showing that how the oxygen fugacity will change in the Earth's interior. So this oxygen fugacity is compared with a log FO2 which is relative to iron woostite buffer, because in the last slide I have shown you that when you go deeper and deeper, mantle is becoming very reduced, so it's better to compare this log FO2 with the iron woostite. So when you go deeper and deeper, there will be a point where this curve will intersect with a nickel precipitation curve. This is basically a dash, this line is a metal precipitation curve. So at this point what will happen, that mantle will started to precipitate the metal phase, and then your fugacity will be very close to the iron woostite buffer. So you see this is a 0, so this is a iron woostite buffer. So your mantle at, let's say, at 8 gigapascal, which is equivalent to your 2,400 kilometer, so at that depth or beneath, your mantle will have a free metal and it will be close to this iron woostite buffer. So we basically try to study few mantle xenolith sample from Vajrakharu kimberlite field in the eastern Dharwar craton, and we try to do this oxygen fugacity profile beneath the Dharwar craton. So these are the few data points from our mantle sample. So we have two different type of xenolith sample. So we have this peridotite sample and we have a eclogite sample, and this dash line is basically distinguishing the graphite to diamond stability field, and this inclined line is basically indicating the oxidized form of carbon, that is carbonate. So most of our samples are plotting just below the FMQ buffer, close to -3 to -4, but this eclogite samples are coming very close to FMQ buffer, so it indicates that the sample is very, very oxidized, and we argue that in this particular location there was some kind of metasomatism, and CO2-rich fluid basically interact with this eclogite sample, and they make this sample very, very oxidized. And so basically we are interested to study this shock meteorite. So basically in shock meteorite what happens that when in the asteroid belt we have an asteroid and there is a collision, a shock wave will generate, and this shock wave will propagate inside the asteroid, and if there is some host rock is basically trapped in this shock melt vein, so immediately in fraction of second this shock melt vein will basically transform to some high pressure and high temperature phases. So in this shock meteorite study, there are two issues people are struggling with. The first issue was at which stage your shock meteorite is basically forming. So initially Algorezi and Stolfer, they fight a lot, and later they come up with some intermediate shock stage. And so there is a shock stage from 1 to 6. So if you have a certain feature, based on identifying that feature, you can basically predict that you have what kind of stage your shock meteorite is. Then the second important point is that when we study the shock meteorite, so many times what we notice that we do not have any high pressure phase, and people are struggling for a long time that why we do not get a high pressure phase in the shock meteorite, but in shock meteorite we are getting a bridgemanite. So this is a very messy diagram, but the takeaway point from this diagram is that when we have a melt, this shock, after shock we have a hot melt. So basically that melt is in contact with your host, and host is relatively cooler. So what kind of path they will follow, that will depend on how much melt after shock this meteorite is generating, and basically your melt is at which position. So if your melt is very close to the host rock, so for example we have a 25 GPa, some melt is there, and this melt is in contact with some host rock which is relatively colder. So what will happen that there will be a heat transfer will immediately take place, and there will be a drop in temperature, and after it reaches at this point, so it will basically decompress, and then this will give you this shock temperature. So basically if your post shock temperature is for different minerals, people have basically calculated. So for bridgemanite, if this temperature is more than 400 degree K, so you are not going to get bridgemanite in your sample, even if you have a shock metamorphism in the meteorite. So there are some other phases, for example ringwoodite, which is more robust. So basically if you have any trend you follow, okay, and depending on the final destination, it will decide that you will have a high pressure phase in your shock meteorite or not. So we basically studied this meteorite from Kathol, and what we noticed that near the melt vein we have noticed some bridgemanite, okay, and this bridgemanite has a composition of this composition is very close to the composition what we basically get for the high pressure experiment. So the second thing what we did, we try to measure the oxygen Fe3+ in this sample, okay, and using a TM analysis we basically measure the Fe3+ by total iron in this sample, and this Kathol bridgemanite has this Fe3 by total is close to very similar to what Dan Frost has produced in his multi-anvil experiment. When we compare this composition, the composition of the Kathol bridgemanite with the two other results, so what we have noticed that Tenham also has a bridgemanite, but in this bridgemanite there is no aluminum, but your lower mantle has almost 5% of aluminum. So there is another result by Luca Bindi and others, and they have also reported this iron-rich bridgemanite, this very, very iron-rich, and in mantle we do not have a 50% of iron. So our composition is very, very close to the composition which people are generating using a multi-anvil press, and these Fe3 by total iron is also very, very close to what experimentalists have basically produced. So we try to compare our result with the natural samples. So x-axis is a Fe3 plus in the bridgemanite, and y-axis is your unit cell volume. So this is the terrestrial samples we have. We have only 3 terrestrial samples, and so this slope is relatively steeper compared to your synthetic sample. So what we have argued here, that because these samples are formed at a very high temperature, and because of that you have a higher this unit volume, and also your terrestrial sample is more sensitive to the Fe3 and aluminum 3 plus these trivalent cations. So we have suggested this, and then I think I'll skip this one. We have another meteorite in which we recently got the bridgemanite, and so yeah, so this is the conclusion. Yeah.
Thank you, Professor Ghosh, for concluding in time. So, questions from the audience are welcome. So, any question?
While we're waiting, but there's a question.
When you are showing that one particular data where the meteorite is the melt is formed in contact with some host rock, you are showing. So my question is that when a meteorite will hit the host rock, won't the host rock also melt?
No. So basically, if you see this diagram, just a minute. So you have a host rock. So in this host rock, the temperature would be relatively very, very low, and it will be colder. So you will have a localized melt pockets where you have a very, very high temperature. And in this localized melt pockets, if there will be some host rock is trapped, so that will transform to the high pressure. So this is the pressure release path for the host rock, and this is the pressure release path for your melt vein. So there is a huge difference in temperature. So this part there will be no melt vein.
But when we see the impact craters, for example, if you see this Dhala crater or any other major impact crater, people are reporting, say, rocks like spheroid or some other melting, or even some types of pseudotachylite, which are supposed to be molten because of the shock. It is basically within the host rock itself.
So basically here,
I think that is a decompression melting kind of.
Yeah, so here also you have a decompression melting. So what kind of path you will follow, that is a different question. Like you can take a path from here to here, you decompress, and then you follow like this. The point here is that your final this shock temperature is coming to this gray area or not. If it is coming to this gray area, then there is a high possibility that you are going to lose that high pressure phase, and because of that all shock meteorites are not producing high pressure phases. Yeah.
Thank you.
Thank you, sir. So if there are no more questions, we will move on to our next talk.
Thank you, Shuja. So the next talk is by Rishit Ruj, Polygons on Mars, Insights from Periglacial and Evaporative Analog Studies. He's from the Okayama University.
This pointer. You can use this one too. Then you don't have to turn back. Which one you want?
Both, maybe.
This was light changer, and this one
Okay. Okay.
Do we need to shut it off or?
It's okay. It's okay. So, good morning, everyone. My name is Trishit Ruj. So, I am an associate professor in Okayama University, and this part of the research I am going to show is by my student Takaki Sako. And we have worked on polygons of Mars, and this time I will be presenting that research. So the reason we started working on Mars is in this project mainly on polygon because of in a target where we are going to have human exploration in the future, and for the human exploration we need surface ice. And in the surface, but in case of Mars, the surface ice is preserved only on the high latitude region. But in case of landing mission, high latitude landing is not possible in case of Mars because of low atmospheric coverage. So we had to find a location in the mid latitudes. And for that, this project started, and here we started to find ice deposit on the mid-latitude region. And I am a co-PI of Japanese Mars mission to select the landing site, so I get involved into this project. So for this human exploration mission, the initial purpose of us is to find the location where we can get maximum highest volume of ice preserved, and we had to look at the location where we can get the ice at minimum excavation depth. So the minimum energy needed for the ice to extract from the surface. And then what method we used, because we don't have much knowledge on the surface of Mars, so what we used is used a Mongolian field survey result and compared with another satellite survey in the Arctic region, and then applied this knowledge to Mars to identify the location of highest or most voluminous ice deposit on Mars. So this is a field photograph, drone image from Mongolia. So you can see the scale. Here we are here, and these polygons are very larger in scale, like 30 to 50 meter. And when we went to the field, just a field, and we could not see anything. So that's why we had to fly the drone, and then we can find the structures. And in case of Mongolia, we find different kind of periglacial morphologies. For example, polygons. Polygons are formed by the freeze-thaw mechanism of seasonal melting and seasonal crystallization of ice. This is an example from Mars, and this is an example from Earth that we find in Mongolia. Then we find pingos. Pingos are ice-cored hills like this. This looks like ice-cored hills in Mars, and this is a ice-cored hill in Mongolia. Then another periglacial structure that we find in Mars is called brain terrain, but this brain terrain was not reported from Earth, so we find this in Tariat, Mongolia. Then we choose Mongolia because it's one of the regions on Earth where the periglacial morphology has changed from continuous to isolated to there are boundaries where in the last periglacial, last high glacial time, this boundary was shifted more towards the south. And in Mongolia, we started from this North Mongolia, where the permafrost is more continuous, to then went further south to almost to the Gobi Desert, and find this 5 type of polygons. Mainly is a low centered polygon. You can see from the name, you can see that there are centers which are lower, and the fractures they are more higher in the elevation. Then we see from the transition from low centered to high centered polygon, and then with time and when it went more south, it became degraded, then eroded, and then became isolated pit. So this is a chain which started near the on the northern part to low centered polygon. When we moved towards the more south, it became like the isolated pit type polygons. And then we applied this, and then we also find like pingos in Darhat Basin and Tariat, and also brain terrain that we first time reported on Mongolia. And this is very consistent with the distribution of the polygons on Mars. Then we used this knowledge to understand the satellite the survey of Mars. And in case of Mars, what we did is our student did analysis of all the polygon and identified all the polygons from 30 to 42 degree latitude, which is the landing window region of Mars, and identified different kinds of polygons. And based on these different kinds of polygon, he was able to find the location where we have higher rich zone of ice. There are two rich zone of ice, there are medium zone of ice, and then there is less ice rich zone. And then we also compared this our result with the annual ice budget, and our result is very much consistent with the annual ice budget as well. And this result we published this year in JGR Planets, and this is the paper. So this is the part of the research we have finished, and this was our goal. But while doing this research, we find there are other types of polygon, and they did not look like to be a polygon that formed by periglacial processes, so which resemble more like a desiccation polygon. Desiccation polygons are formed on arc lakes where during the evaporation process, when the water evaporates, and then desiccation kind of polygon form. In case of Mars, we find this kind of desiccation polygon at low latitude, and then there on the higher latitude, on the crater floor, we find these another two types of polygons. So in case of Mars, this liquid water does not exist at the present day atmospheric condition, but this is a data from Phoenix landing site location, and you can see at a certain point, certain time of the year, liquid brine can exist on the surface of Mars. So understanding this, taking this into consideration, we started to find the environment on Earth where we can find the desiccation polygon, and these are the locations where the desiccation polygons are very much reported on Earth. And this year, last year, in July, we traveled in the US, southeast US, and almost 10,000 kilometers. We drove around there and encountered like 22 sites. And from there, we find three different types of polygons. Mainly is called raised rim polygon, when the rims are more raised, and these are like here at 10 meter of diameter, and they become reddish colored because of the presence of cyanobacteria. And then we find another one, this is sinuous depression polygon. We see sinuous depression here and there, and then these are the salt boundaries, and they are bigger in scale than the raised rim polygon. Then there are another polygon we find is low rim polygon. Low rim polygon are large in diameter, like 50 meter diameter, and then there is elevation between the rim and the central part of the polygon. These polygons that we find in case of Earth are very similar to that we find on Mars. So using this polygon and their environmental condition when they are formed and where they are currently at this moment, we try to understand the possible mechanism, the formation on Mars. So one of the case I am showing it here is from the Winnemucca Lake. It's from Nevada, and where we did some we collected some sample because we cannot enter into the lake because it's still very saggy at this moment, and so we did some ASTER data analysis, and we find this raised rim polygon where the liquid water is available throughout the year. And it has the higher amount of salinity. Then we find sinuous depression polygon, which is a bit far from the central part of the lake, and then they are more gypsum and carbonate rich. And then we found on the lake boundaries they are low rim polygons. And so what we find from this is the high rim polygons are formed in more wet environment where liquid brine or liquid water is more available. Then sinuous depression polygon are formed in where the water is available once a year or sometimes during the rainy season. And low rim polygons are formed in a region where this is more drier environment. When we move from here to this direction, we are finding more drier environment. And in case of low rim polygons form when the water level is high during the high flood in every 10 to 15 years. And the composition we find where high rim polygon is more halite rich, and then we find gypsum in the sinuous depression polygons. And now we are not sure from the ASTER data what kind of mineralogy is in the low rim polygon. So we are trying to assess it in the further studies. So what we started is like from the polygon research is to identify the location of high water storage. Then and as a side product, we find the next part of the Martian mission of Mars to find an environment where liquid water was available. So we started from this one this year, and then we moved to the next water-rich environment. We are moving towards the research toward finding more water-rich environment where life can survive at extreme condition. And my PhD student is joining this year, and she will take up this part of the research. So in a conclusion, we find the location from the polygon research, the Amazonis planitia and Arabiata. These are the two locations that I marked in the circle. It's more ice rich than the other part of the Mars, and these are the possible location for human exploration. And we found there are different types of desiccation polygon. In case of Earth, they are morely on the lower mid latitude to lower this region, desertic region. But in case of Mars, they are more on the higher latitude region. So this is our current understanding at this moment, and we will take forward to in our next studies. Thank you.
Thank you, Trishit, and thank you also for staying on time. Questions? Yes, we have 1 minute.
Hello, very interesting study.
Thank you.
So I just wanted to know regarding these sinuous polygons. There is gypsum in the substrate, isn't it?
Yeah. Yes.
So in which form the gypsum exists there? Meaning, is it is there Barwick-like crystals, primary gypsums, or Shackle's-Barr? That is the question.
We could not get the samples actually. What we got is from the ASTER data. Okay. So it's the remote sensing data at this moment. We could not collect the sample from the basin because we are unable to reach there.
I understand because sometimes Shackle's-Barr they are related with fracturing.
Okay, yeah, okay. Thank you.
Any other questions? Yes.
Just a query. What could be the formation mechanism of these polygons? I mean, are they like desiccation cracks?
There are two types. These are the desiccation cracks, and the other one that I show in the first part was because of the freeze-thaw mechanism. There is an expansion of the volume and then the decrease of the volume, and to subside that one, then the cracks formed.
So that's why the polygonal cracks form.
Polygonal cracks are forming. Yeah.
Bulk contraction.
Yes.
Oh, thanks.
Any other questions? So, I have a question. So, so the nature of the crack and the geometry should depend on the substrate temperature and the rate of diurnal variation.
Yeah.
And that's very different on Earth and Mars.
Yeah.
How well do you think you can translate your observations on Earth to Mars?
Yeah, this is a very good question. So what we get in case of Mars is like 5 to 6 times higher polygonal diameter in case of Mars. So the three things we are currently thinking at this moment is due to that is like the environmental condition, then humidity and low temperature rate, low temperature of desiccation, low rate of desiccation. And then another possibility can be related to lower atmospheric pressure. Mars has very low atmospheric pressure. Then another possibility, and we don't know how is it if it is affecting or not, the gravity. Martian gravity is 1/3 of Earth, so that can also affect. So the gravity we cannot do, but now I am building a Martian pressure temperature control environmental chamber. So we in next year maybe we will start doing some experiment into the chamber and try to see how it is different on Earth and how different is it on Mars.
This is also very amenable to modeling studies. Do you plan any modeling work?
Sorry?
This is very amenable to modeling studies. Do you plan any modeling work?
Yes, we will try to do, but not mathematical modeling, but more like physical modeling, analog modeling. Yeah.
Okay.
Yeah. Thank you. Thank you.
Thank you.
Thank you, Trishit. So our second last talk of the session will be by Urmi Datta from Patna University. I request Dr. Urmi to deliver the talk on core-mantle coupling, insight into early Earth dynamics through numerical models.
দোকানের সামনে হেলদি অ্যান্ড টেস্টি রেস্টুরেন্টের সামনে দাঁড়িয়ে আছি। আমি তোমার নাম্বার পাঠিয়েছি, কল করে বুঝতে পারছি।
Right. ভিতরে
Hello. Hello. Good afternoon, everyone. First, I would like to acknowledge the organizers, especially Professor Shankar Bose sir, for inviting me to present my work here. Today's topic is not visible here. It is core mantle coupling, insight into early Earth dynamics through numerical models. Can you zoom out the slides? This
ফুল স্ক্রিন আসছে না এই যে সেটিংই এরকম হয়েছে।
ওকে, নেক্সটগুলো তখন
এটা আসবে নাকি?
ঠিক আছে, ওকে ওকে। This work has been done in collaboration with Dr. Ashley Willis, who is a senior lecturer in the School of Mathematical and Physical Sciences in the University of Sheffield, UK. As we are talking about the early Earth, just for a quick recap, our Earth formed 4.6 billion years ago as a part of the solar system, and one of the early processes in this Earth formation was accretion, where planetary bodies of different sizes collided with Earth. And as Professor Sujoy Mukhopadhyay has discussed early this morning, that Moon was formed by such a giant impact. So, Ruby et al. In their work on different mechanisms of core formation, they, according to them, the giant impact caused a very large-scale melting on Earth, where the undifferentiated Earth, which was made of metal and silicate both, molten together, and then the metals being heavier segregated at the base, and finally we got a silicate magma ocean enveloping the liquid core. Labros et al. In 2007, they worked on the fractional crystallization of this magma ocean, and according to them, the crystallization started from top to bottom, and finally a basal magma ocean could sustain, just covering the core, and subsequently this slowed down the cooling of the core. And in a separate work by Pozzo et al., where they used DFT calculations of liquid iron at the pressure temperature condition of Earth's core, they found that the thermal conductivity of Earth's core is much higher than previously estimated. So together, both these works, they predicted that the age of the inner core cannot be more than 1 billion years. So the question is, what happened before the formation of inner core? Because it is an important question, because the solidification of inner core is the reason behind the convection, chemical convection process going on inside Earth's outer core. So before the inner core, did the outer core convect at all, or the question is, how did the geodynamo work if the outer core did not convect? Because we have rock records that show that magnetic field is as old as 3.7 billion years. So this puzzle is labeled as new core paradox by Peter Olson, and he suggested that the solution may lie in searching for alternative sources to drive the outer core convection. So there have been a few works for this search, ranging from subduction related heat flux at core mantle boundary to silicon magnesium precipitation inside core from the mantle. And in this work, we are trying to see whether the core mantle coupling can supply the energy source to drive the core convection. For this work, I have used the Leeds geodynamo code, which was developed by my co-author Ashley Willis. This code is mainly used for studying the planetary dynamos, and here the fluid layers are generally considered in rotating spheres and spherical shells. For this particular work, this Leeds dynamo code has been modified to exclude the magnetic field calculations. We are mainly focused in the hydrodynamic calculations here, that is the velocity and temperature of interaction between the magma ocean and core fluid layers. And these core and magma ocean fluid layers is considered as concentric spherical shells in a rotating frame. And we are aiming to study the effect of different parameters for thermal and viscous coupling. These are the two main important governing equations for this study, Navier-Stokes equation and energy equation. These two here are in the dimensionless form, and it includes, they include different important dimensionless parameters like Ekman number, which represents the effect of the rotation on fluid layers. Next is viscosity ratio, then we have thermal expansion coefficient ratio, then Prandtl number, which represents the thermal diffusivity in fluid layers. Next is the Rayleigh number, which represents the turbulence in fluid layer. Next is thermal diffusivity ratio, and finally density ratio. This is the parameter values we got from literatures, and we use this for this study. This is the model, three-dimensional model, and these are the boundary conditions. And we performed a linear stability analysis and found that the Rayleigh, critical Rayleigh number for particularly this system was 4.7. So as I said, we aim to see the effect of various parameters. So let us start from see the effect of change in Rayleigh number. Rayleigh number, we start with 20, which is almost 5 times supercritical, and here we can see that the magma ocean is showing organized convection, but in the core there is little flow. But as we increase the Rayleigh number, we can see the flow turbulence increases in both the layers. Here the colors show the velocity values where the maximum and minimum values are at the top. So we can say that the more supercritical the flow is, more is the chance of induced convection in the core. Next, we see the effect of increasing thermal diffusivity ratio. So now you can think that increasing a ratio can be achieved by increasing the this is ratio O by C, that means ocean by core. So we can increase the ratio by increasing the value of K within the ocean, and K here is thermal diffusivity, which is proportional to thermal conductivity. So we can say that presence of a highly conductive layer at the top of the core may suppress the core convection. At K O by C 0.5, we are getting low core flow than the lower value of this ratio. Next, we see the effect of decreasing viscosity ratio. This ratio again can be decreased by, we can imagine if the magma ocean itself has low viscosity, then the ratio drops. And we can see as the maximum minimum value shows that as the decrease of viscosity ratio, more is the flow is more stronger. So you can say the presence of low viscosity layer at the top of core may promote the core convection. Next, we see the effect of change in magma ocean thickness. Depending on how big the impact was, or where we are at the crystallization history, the depth of the magma ocean can vary. So here you can see that as the depth of magma ocean increases, the flow becomes stronger, and it is as the values suggest that it is as stronger as the just the viscosity drop case. So we can say that a thick high viscosity magma ocean will convect almost as strongly as a low viscosity thin magma ocean. For the time constraint, I have included only one temperature plot here, which is for our standard model. And here you can see formation of thermal plumes at the core magma ocean boundary or core mantle boundary for this case. This formation of thermal plumes indicate fluctuation of heat flux within magma ocean. And there is a theory that the ultra low velocity zones or the large low shear velocity provinces are nothing but the remnants of this ancient magma ocean. So if they are indeed, then these zones must also have similar flow within them. And these high flux, heat flux zones may be the source of mantle plumes. So to summarize, we have critical Rayleigh number for the rotating concentric core magma ocean system is 4.7. The more supercritical the flow is, more is the chance of induced convection in core. Presence of highly conductive layer at the top of the core may suppress the core convection. Presence of low viscosity layer at the top of core may promote the core convection, and a thick MO will convect almost as strongly as a low viscosity magma ocean. But whatever the case is, we can see the magma ocean is always dominates over the core flow, or you can say that the convection starts in the magma ocean, then it induces the flow in the core. So it can be said that the convecting magma ocean can supply the energy for core convection in early Earth, and we can also suggest if the magma ocean has high electric conductivity itself, it can generate the magnetic field by running the geodynamo. And lastly, the investigation of full magneto-hydrodynamic studies or dynamo studies is needed for this particular configuration. Thank you.
Thank you, Dr. Urmu. Thank you for concluding within time. So if there are any questions from the audience, please. So first one question, Dr. Manda.
Urmi, very good presentation.
Thank you, sir.
Question is, how much melt is there in the ultra low velocity zone?
That
Even is the remnant of magma ocean. Any idea?
Maybe 1 or 2%. I'm not sure.
So
sir.
why not that generated due to incipient melting rather than remnant?
It also can be, sir. I said that this is one theory.
Okay. Thank you.
So, no questions. I have one. So you didn't study the effect of thermal expansivity. Now that is expected to change with depth.
Sir, I have slide. Sorry. This is the result of thermal expansion coefficient, and this exactly actually follow the effect of Rayleigh number, how the Rayleigh number changes. Only for low Rayleigh number, we are seeing almost no flow in the core, but here at low alpha, we are getting some flow. So this is actually the Rayleigh number includes the thermal expansion coefficient. So these two have similar effect.
And would it matter if there's a gradient in the thermal expansivity?
Sorry?
If there's a gradient, if it's not constant within a layer?
Maybe,
that
sir.
would be worth trying because thermodynamically you expect it to change with depth.
Sure.
So, thank you.
Thanks.
So, okay, again, and we move on to the last one. Dr. Palendu Halda from IISc Bangalore, and he'll be speaking on radiogenic strontium isotopes in diamictites record weathering and growth of continental crust. Palendu.
চেঞ্জের জন্য আর লালটা টিপলে হচ্ছে পয়েন্ট করার জন্য ঠিক আছে
Well, good afternoon, everyone.
So today I'll be speaking on how we can use radiogenic strontium isotopes in glacial diamictites as they record weathering signatures and the growth of continental crust. A brief introduction. So we live in a differentiated Earth, right? We have a core, a mantle, and a continental crust that has been extracted out of the mantle. The continental crust is volumetrically very insignificant, comprising about below 0.6 volume percentage of the entire Earth. And this continental crust is further compositionally subdivided. We have a felsic upper crust, a felsic lower crust, and a mafic lower crust, each present in a ratio of 1:0.6:0.4 by volume. And the felsic upper crust can constitute up to 60% of incompatible mobile elements of the entire planetary budget. Now, since the formation of the continental crust, whenever it might be, there's a gradual change in the composition of the continental crust in itself. On the y-axis, we have the rubidium by strontium as it has changed over the age of the Earth in crystalline rock record. What we do see is that there's a stark difference in the early and the present day, where we can see that the early Earth, the crust was dominantly mafic, which is shown in the low rubidium by strontium ratios, and it slowly fractions to more rubidium by strontium ratios. This is from a crystalline rock record. But can siliciclastic records mimic this change? For that, we have the in-place crustal rocks, which can be disintegrated by physical processes, where ice sheets, when they traverse over continents, lead to deposition of the sediments in low-lying basins. And this gave birth to the $1 million idea, when Victor Goldschmidt in 1933 first postulated that the glacial sediments are derived during cold and dry climate, which means the effect of chemical weathering on these samples are supposed to be minimal, and therefore they can be excellent archives to estimate the composition of the UCC. And nearly 200 years after, geochemists have started working on this idea, and they have seen that glacial diamictites can be a very fruitful archive to look into the evolution of the composition evolution of the UCC, the chemical weathering history of the UCC, the onset of oxidative weathering, and even the growth of continents, in this case Africa and Americas, and the modern day stable acidic composition of the UCC in terms of its magnesium, silicon, or vanadium isotopes. With this, we pose some outstanding questions. How has the composition of the continental crust evolved over time? And what could be the efficacies of these crustal archives in estimating the crustal compositions? Our choice of tracers are radiometric rubidium and strontium systematics coupled with the samarium and neodymium systematics. We used the ICP-MS for geochemical analysis and the TEAMS for the isotopic analysis. Coming to the archive, glacial diamictites, what are they? They are poorly sorted sedimentary aggregates which are derived from the abrasion and the erosion of the continental crust. The photo on the left is a Dwika glacial diamictite, a Paleozoic glacial event in South Africa. Now, multiple diamictite samples were collected from each formations, and they were converted into composites. The clasts were excluded, and the matrix were finally powdered and homogenized. And these come from 24 different locations spread across 4 different continents, and they occur across 4 broad geological events: the Mesoarchean, Paleoproterozoic, Neoproterozoic, and the Paleozoic. We'll use the same color coding for all the figures in the next slides. When the first glacial diamictites were analyzed in 2014 by Gashnik, it came as a major roadblock. What could be seen here is that the glacial diamictites carry a high chemical index of weathering number, which means higher CIA corresponds to higher degree of chemical weathering, which is against Goldschmidt's original postulate that this could not have any chemical weathering signatures. With this, we arrive to our results, where we have done the radiogenic strontium isotopes in these glacial diamictites and plotted across sedimentation age. What we can see is that we see a great variability in the radiogenic strontium isotopes, ranging from almost 0.704 to 0.97, and the spread decreases with the younging depositional age. But when we tried plotting the initial strontium isotope composition as a function of its sedimentation age and the model age, this is when things got really interesting. We could see that most samples are plotting below the bulk silicate earth evolution curve, which is improbable or rather impossible. And this could only be possible if the parent by daughter ratio, in this case the rubidium by strontium, has fractionated or been perturbed by the post-depositional weathering changes, which means the glacial diamictites carry both pre and post-depositional weathering change. But how do we correct for this rubidium by strontium ratios? We use the amalgamation of both rubidium, strontium and samarium systematics to arrive to a parameter called the time integrated rubidium by strontium ratios, which is nothing but the ratio required to generate the present day radiogenic strontium acidic composition since the separation of the crustal material from the mantle. And most importantly, this time integrated ratio does not carry any weathering signature but records the rubidium by strontium of the crystalline crustal rocks. Using this, we derive three more parameters. The first, the cap rubidium by strontium percent, which is the deviation of the measured rubidium by strontium to that of the time integrated ratio in parts per 100, giving us the extent of weathering. The second being the rubidium by strontium time integrated parameter by itself, and the third, the corrected 87 strontium by 86 strontium at depositional age. We look into all these three parameters and look into the secular variations. First, the cap rubidium by strontium. Overall, the measured rubidium by strontium ratios is far more than the time integrated rubidium by strontium ratios in most samples. And the higher rubidium by strontium ratios implies the loss of strontium during chemical weathering. The extent of strontium loss does vary, as can be seen on the figure on the left, which is the plot of time integrated ratio, that is no chemical weathering signature, versus the measured rubidium by strontium ratios. If there were no chemical weathering signatures, all the samples would have plotted on the 1:1 line. But what we do see here is a negative deviation from this. And the loss of strontium is higher, in fact, in the younger glacial diamictites, the Neoproterozoic and the Paleozoic diamictites, compared to the Mesoarchean and the Paleoproterozoic. The cap rubidium by strontium ratio when plotted over sedimentation age shows some sort of variation, or secular variation, where it's higher for the Neoproterozoic and the Paleozoic diamictites, and when plotted on the background is this curve of normalized riverine runoff, which means which shows the extent of strontium that's been carried into the oceans due to chemical weathering. These peaks, the dotted peaks, show the periods of high chemical weathering, and this corresponds to also the supercontinent cycles. And luckily our glacial diamictites in the younger samples correspond to the Gondwana and the Pangaea period, which means the supercontinent amalgamations, which could be associated with higher relief, increases the rate of weathering, and therefore higher strontium loss from the continents to the oceans. The second parameter, the time integrated variation, rubidium by strontium variation. Again, this ratio has no weathering signature and carries the signature of the crystalline continental crust. The rubidium by strontium ratio varies over time and reaches its peak in the Paleoproterozoic, and then progressively decreases from the Neoproterozoic and the Paleozoic. And this is almost similar to Duim et al. 2015, which showed the rubidium by strontium variation in crystalline rock records. But what could be the cause of this variation? We look into both geochronological and geochemical evidences. First, if we look into any global cratons, its felsic stratigraphy is fairly monotonous. We have TTGs which slowly grades into sanigitoids, and then comes the more fractionated granitoids, which could compose of biotites and two mica granites, and the hybrid granitoids. And interestingly, the rubidium by strontium ratio increases from the TTGs to the hybrid granitoids. An example from 3 cratons, where we see that the Mesoarchean glacial event would have sampled only the low rubidium by strontium TTGs when compared to the Paleoproterozoic glacial events around 2.4, which had the option of sampling of more fractionated felsic lithologies. And therefore, this variation in time integrated ratio records a shift to more felsic composition and might indicate a change in the growth pattern of the continental crust. Geochemically, the derivation of these felsic rocks, these granitoids, mostly results from intracrustal melting. Evidence of intercrustal melting can be found in plagioclase cumulates in the middle or the lower crust. And when we plot the strontium by strontium star and europium by europium star, where both these elements are compatible in plagioclase, we see that only the Paleoproterozoic glacial diamictites show a good correlation between the strontium and the europium anomaly. The other three ages do not show any covariation. Therefore, this variation in rubidium by strontium in time integrated ratio records a shift to more felsic composition of the continental crust. The third parameter is a secular variation of the time integrated 87 strontium by 86 strontium, which is the initial corrected radiogenic strontium isotope composition at sedimentation age. The radiogenic composition increases from the Mesoarchean to Paleozoic, which corresponds to which nearly agrees with the 87 by 86 composition of the UCC at 0.73. But this radiogenic composition is a function of the rate of extraction of the mass from the upper mantle and the rate and the time at which these were extracted. Now the continental crust growth models, there are a wide plethora of models which could broadly be subdivided into 4 categories: the exponential growth model, the rapid growth model, the punctuated or the delayed growth model. We now tried modeling which growth model could best fit this present day estimate of the radiogenic strontium isotopes. We see that the exponential growth model derives a similar value to that estimated by Weiser and Mackenzie in 2003 and from our results using the glacial diamictites. The numerical models predict that at least 60% of the continental crust had been extracted out of the mantle by Paleoproterozoic. Next, we look into the neodymium isotopic composition of these glacial diamictites and correcting for the erosional bias and the topographic effect. We can see that on the figure on the right that at least 65% of the continental or 50% of the continental crust was formed by Paleoproterozoic compared to around 65% from numerical methods. To summarize this entire research, we can say that the glacial diamictites have suffered weathering both pre and post, and there could be up to 90% of strontium loss, which contradicts to other studies by Gashnik et al. In 2014 and the original postulate of Victor Goldschmidt. The time integrated ratio, the rubidium by strontium and the radiogenic strontium isotopes vary with time and they record crustal differentiation. The Paleozoic diamictites approximate the present UCC values both in terms of its rubidium by strontium ratios and the radiogenic strontium isotope composition. The exponential growth model, in contrast to the delayed and the punctuated growth model, best replicates the present day UCC composition. And the neodymium isotopic composition in the diamictites say that at least 50% of the crust had been extracted by the Paleoproterozoic. Thank you, and any questions?
Thank you very much, and we have time for questions.
So, how did you calculate the strontium modelage? Because there may be multiple crustal reworking events in the crust.
So I'm not calculating the strontium modelage. So what I'm doing is I'm trying to derive a time integrated rubidium by strontium ratio. Because as I showed in the initial slides, that the rubidium by strontium ratio by itself is perturbed. So I cannot come to a fruitful modelage. But when I'm looking at the neodymium isotopes, I know it's means the extraction time from the mantle. So I have an evolution diagram, and then I take a 2-stage evolution of the strontium isotopes from that point, and I amalgamate both to come to a crystalline rubidium by strontium ratio. In short, I'm not deriving any modelage from the strontium isotopes.
Okay. So in your database, do you have any diamictite from India?
We don't have, but I tried going into fields. The Dharwad Creton was the most accessible, but I'm not really convinced that it's a diamictite product, so we didn't go into that. But we rather stuck to the samples which had been previously published, so for better comparison of our results.
Diamictite from which formation? Which?
So we have diamictites from the Mesoarchean samples are also.
I'm talking about the Dharwad.
The Thalia conglomerate, that's
There
what.
is a lot of controversy. You can try even the Gondwana here.
That could be, and we can further expand this, but I'd rather stick to the original samples.
Just one more question here.
I was just reiterating his view because I know that there are dimectite in Gondwana, in fact in the Darjeeling Sikkim Himalaya. I think you can try with that if you want to. That's my just.
Yeah, of course, means we certainly do that.
Okay, thank you.
Any other questions? So I have one.
Yeah.
So can you distinguish, you can calculate how much net crust was extracted, but can you distinguish whether more crust was extracted and recycled versus whether it was primitive extraction?
So if you're following the methodology laid by Allegro and Russo in 1984, so what they have done is that they've introduced a parameter called the K, which corrects for the erosional bias. So that essentially takes into factor topography. But if you're looking into how much of crust has been recycled, I'm not quite sure that we could do that from our data. But since I'm talking of the time integral ratio, so this is more of juvenile crust that has been extracted out of the mantle.
The question is whether you can distinguish between the exponential and the recycled crust growth models with what you're doing.
I need to think about that. I haven't really thought here.
It'd be worth checking it, right? Because those are the two that people are discussing now. So
right.
To see how we can do that. Okay. There are no other questions. I don't see any hands.
Thank you.
So I'd like to thank you and all the speakers in the session, keeping to time and doing everything. And then I think with some delay, all of you have earned your lunch. And I don't know, the organizers can say when we start the next session.
Chairs, Professor Sumit Chakraborty and Dr. J.K. Thompson, as well as all our speakers for their insightful contribution to this session. I would now like to invite Professor Santanu Bose onto the dais to present mementos to our session chair and our keynote speaker, Professor Sujoy Mukhopadhyay. May I request Professor Sujoy Mukhopadhyay to come onto the dais. Thank you, sir. With that, we officially conclude the technical session 3. Thank you all for your participation. Before we move to the next session, we will take a lunch break for 1 hour. We will again reconvene here at around 3 p.m. Another announcement I want to make here. Dr. Ranjit Iyer, from technical specialist from Oxford Instrument, is there in our ACM lab for EBSD analysis demonstration. So the participants, if interested, can visit there during the poster session. Thank you.
হ্যাঁ হ্যাঁ আচ্ছা আমরা দিয়ে দিচ্ছি হ্যাঁ কভারগুলো আমি দিচ্ছি কভারগুলো দেন কভারটা
This session is entitled Shallow Crustal Processes, Landform, Evolution and Neotectonics. Now I like to invite our session chairs, Professor Harendranath Bhattacharya. He was the former HOD of this department and presently associated with the Techno India, and Professor Ramananda Chakraborty. He was our ex-student and presently he is placed in IISc Bangalore. Now I like to request our chairs persons in dais. Sir, please take your seats. Now I request our student to formally welcome our chairs by presenting flower bouquet. We are happy to announce that for these sessions we get our keynote speaker, Professor Shubhi Sarkar from Jadavpur University, and please be noted for your maintaining this time schedule. Presenter, keynote speaker will get 20 minutes time and presenter will get 15 minutes time, including the oral presentation and discussion. So I like to hand over this mic to our chairpersons.
Hello. Good afternoon. We are going to start the last session of this today's seminar, and the title of this session is Shallow Crustal Processes, Landform Evolution and Neotectonics. Professor Shubhi Sarkar of the Department of Geological Sciences, Jadavpur University, will deliver the keynote address. And I request Professor Sarkar to come on the dais. Professor Sarkar, please. The title of Professor Sarkar's lecture is Surface Processes and Preservation Bias, a journey from Phanerozoic to Precambrian positional reserve.
এটা দিয়ে স্লাইড চেঞ্জ হয় আর এটা দিয়ে পয়েন্ট করতে পারবেন, ঠিক আছে? সাপোজ
এক মিনিট দেখে নিই।
এটা দিয়ে হচ্ছে স্লাইড চেঞ্জ হবে, এটা দিয়ে পয়েন্ট করা যাবে।
এটা পয়েন্ট আর এটা
স্লাইড চেঞ্জ। ওকে, হ্যাঁ, যদি অসুবিধা হয় আমি এখানে করে দিচ্ছি, তাহলে আপনি কম্পিউটারে ডাইরেক্ট করতে পারবেন।
না, আমি এখানে
শিওর তো? ওকে স্যার।
Good. Hello. Okay, I'm Professor Shubhi Sarkar from Jadavpur University. At the beginning of my lecture, I like to convey my regards to the father figure of geology, Professor A.K. Shah of this university, in fact, this Presidency College. And we, during our
childhood of geology, we used to see him from very far away, and he was a man who inspired many, many scientists, geoscientists of India. So my regards to him. And today I will talk on surface processes, but not on surface processes directly, the interaction of surface process and biota, and what's their role in sedimentology. That I will discuss, okay? So, my intention is to present a brief overview. Second thing is share my observation made both field from modern and ancient environment, and acknowledge my proud inheritance, my association with Jadavpur School of Sedimentology. And of course, I should convey one thing. This has been started with the person sitting in my lap, Professor H.N. Bhattacharya. So, surface processes really are perpetual. And the interaction of biota during the Phanerozoic and the surface process is quite well known. And of course, because of this interaction of biota, we misses many things. We misses many things in the sense they destroy primary sedimentary structure, which is a key element of sedimentology. But at the same time, sometimes they compensate the loss. As for example, if you see, this is a photograph from modern sediment, Chandipur, Odisha coast. You see the interaction of biota on a surface of a ripple flat, almost destroy the ripple surfaces. But you can have some idea about the presence of, at least they had been deposited above the sediment water interface. The second figure you see here, this is it's altogether because of bioturbation, only fossil within this Cretaceous bark sediment. But if you look closely, you will find that the orientation of the fossil distinct bipolar orientation. The third figure, it is from which formation Cretaceous of Kutch. It's no structure, nothing is present, only a massive sandstone with plenty of bioturba. This indicate that definitely there was bioturbation, and the sedimentation process definitely was slow. Anyone can tell it is at least not quantitatively, but qualitatively one can speak out that, okay, the sedimentation during that period was very slow. But this interplay between the biota and the surface process is largely unknown in Precambrian. During the Precambrian, of course there was biota, but they were microbiota. So now, during this deep time processes, microbes appear on Earth largely around 3.5 billion years ago. And then the Earth became a biological planet. And then there was many interaction between the surface process and this biota. Biota means this biota, microbiota. So during this Precambrian Cambrian boundary at 542 million years ago, there is a sea change in biotic population. Metazoa replaces the microbiota. So metazoa, when changes this microbiota, then there was a sea change of interaction between the sedimentary surface process and sediment. So now it is very difficult to conceive what was the role of microbiota during the then time, means Precambrian time. What they used to contribute. In fact, if you think deeply, if you can realize the sedimentation ethos of the Phanerozoic time and the Precambrian time was entirely different. In fact, during the carbonate, in case of carbonate precipitation, people believe that, okay, there was a sea change because the Precambrian carbonate and the Phanerozoic carbonates are entirely different from the biotic point of view. But beside this, there was many difference between these two distinctive depositional systems. So now there are many distinctions. I will discuss mainly two aspects: how the biota help this preservation of sediments, and what is their role in sequence building processes. So how it a sequence develop, and ultimately the sequence stratigraphy is governed by this microbiota in case of your Precambrian sediments. So microbial mat colonization, even in modern environment, in protective area, one can get. This is the microbial zonation in a coastal environment, restricted environment in Odisha coast, behind a barge, some swampy environment. There you can get plenty of this microbiota. So now, during the course of lecture, I will cite some example from one from Odisha coast, another few example from Vindhyan sediments, and some from Marwar sediments of Rajasthan. So if anyone can ask regarding the microbiota, people usually say that stromatolite, this is very common in case of Precambrian limestone. These three limestones, from two from Vindhyan, one from a Chinese formation. So this is common, but their presence in the siliciclastic sediment, terraneous sediment, is difficult to establish. But you see, there are their interaction can produce different types of texture, structure, which are difficult to explain in case of Phanerozoic sediment. Here you see there are some sand clasts. These sand clasts form in well-sorted sand, within well-sorted, which is difficult to form. This sand clast, even the sand clasts are curved. So this here if you see, lode cast is formed within the well-sorted sand, and this within this part, you see this is this ripple is not the sedimentary ripple. This is just, this surface has just covered the ripple surface and mimic the underlying surface. So that's why that ripple came into it. This is basically called as palimpsest ripple. It is not original ripple. So this sort of structure in well-sorted sandstone is difficult to explain. In fact, unless and until during my master's or even my PhD, I was not aware how this structure formed. In a well-sorted sandstone, you are getting so many sand clasts. So it's really difficult. Here you see some, in case of carbonate, there is no confusion, because in carbonate sediment, early diagenesis is very strong. That's why sometimes direct preservation of microbiota, same algal filament, bacterial filament, they recognize. So people can easily recognize. But in case of siliciclastic sediment or the terraneous sediment, it's difficult, because usually the microbiota get losses or disintegrate or decay during the immediate after deposition. That's why direct preservation is very difficult. So these are the cracks from different Precambrian formation. And you see these cracks are all within well-sorted sandstone, which is impossible. So a non-cohesive sand, or how can a cohesive material can give you a crack? If you make a crack within a sandstone, immediately it will be just vanish. It cannot be preserved. So, but this numerous types of crack, many of these crack, particularly this one, this is a typical name it has, Manchuriophycus, but this crack many times in literature reported as trespassing. But these are basically cracks formed on sand surface in the Proterozoic time. So these are some figure from a modern sediment from North Sea, and you see this sand actually it make cohesive because of some secretion organism, microbiota secrete EPS. EPS means extra polysaccharides. This is a complex protein, and they make the sediment. Here, some you see some of the sand. This sand has been enclosed within a. They form a coating by the secretion of this EPS or extra polymeric substance. This is the sand. This is not work of mine. This is the work of a German team. They proved that this sand basically make them cohesive by the presence of this extra polymeric substance or EPS. So this is the same ripple, this palimpsest ripple. This is also formed because of this microbiota. You see the top surface, it's not a ripple surface. It's just a cover on the underlying surface, and it mimics the underlying surface. That's why the name has been given by someone as palimpsest. So this, when you see under microscope, you will find plenty of carbonaceous layer, and if you go under ACM, you can find some plenty pyrite along this layer. Huh? So now this give you the proofs. So these are the this slide, if I get time, I will discuss later. Okay. So what is the role of this microbiota in Precambrian sediments? So I noticed one structure has been published in 1974 by Friedman and Sanders in a international sedimentary petrology, then sedimentary petrology, that is called setup. It's almost look like a flute, but flute generally present on the undersurface, it forms on the top surface. So that's why Friedman has given this name setup, just opposite to flute. So he then give this structure's name as setup. Okay, so now setup. So after that, when I joined in sedimentology, I have a question of why this structure never reported from rock record. So when I started fieldwork with my student with different modern fields, particularly in eastern coast of India, I noticed that plenty of this structure form in modern days, but they are absent in ancient rock. There is no record of settle in ancient rock record. So that's why this structure never reported in any common sedimentary book. In the book of Friedman and Sander, they have mentioned like all there, but never ever you see any common sedimentary book. But this structure is very effective. Effective in the sense, this structure formed in the sediment-water interface. You see, in sedimentology, particularly the structure which form in the sediment-water interface, they are difficult to preserve. I know here present Professor Tapan Chakraborty reported some beautiful adhesion ripple form in sediment-water interface. People sitting in outside India, I met some of the people in different times, they mentioned that paper. There's some beautiful photograph from possibly a sandstone from Pranita Godavari Valley. So, because the structure in the sediment-water interface is difficult to preserve. But this structure is abundantly formed in modern environment, but never in the. So I tried to find whether it is possible. Then one realized this structure I got from Sonia sandstone in Marwar. So Sonia sandstone, there this structure is preserved. So these are the setup from eastern and western coast of India. And this advantage of this structure, who are not sedimentologists, sometimes directional structure is difficult to get. Even if you get some crossbreeding, from there getting the direction of flow, sometimes it is difficult. So, but this, if you recognize this structure in the rock record, it is very easy to identify the directional structure. Because the structure you see, a form like this, there is a flaring in, as it is in case of fluid, and there is a stiffer end. So flaring in give you the directional structure. So then when I first recognized this structure in 2004 or 5, so then these are the this set of structure from Vindhyan rocks, Upper Vande sandstone. Plenty of where they present, that is one advantage. Where you are getting a structure, only one structure. In case of sedimentology, if you consider only one structure, it may be or may not be. But when you are getting it in swamps, that is important. So that is one advantage of this structure. So I got this two type of structure. Then I okay, it can be preserved. But why they are preserving only in Precambrian? So I came back to the modern environment. These are the advantage of this getting easily, anyone can identify the paleocurrent direction and all these. So that for a sedimentologist it is very easy. But as for example a geologist not getting a primary structure very straightfully or trough crossbedding on the bed surface, it is difficult for them to measure the direction. Okay, so I thought that there must be some reason. So I noticed that the structure formed on the backshore on a swamp area, there is relatively restricted. You saw microbiota is rare in general environment, but microbiota abundantly present in case of modern Shark Bay or even Yellowstone part. These two things I have not seen, but I have read in book and there are many papers on it, because for developing the microbiota you need some environment, caustic environment. In general environment, the metazoa always dominate over this microbiota. Okay. Oh, so from this, this is you see here the surface where microbiota is growing. They because of desiccation they disintegrate, and those obstacles help to form this this settle. And after the 15 days, again there is a flood tide, and again the surface moisture and the microbial mat layer covered the area. So this may be one of the reasons why they are preserved only in Precambrian record. But it is not possible. So far there is this paper published in 2011. But still not, I have not seen any paper from Phanerozoic. So I think this is the reason why this microbiota, they are preserved only in Precambrian. Okay, this is how they help in preservation, and so possibly settle preservation in Proterozoic, no surprise. And I think Proterozoic time is the best time to preserve this settled sediment. And this picture, as time already passed, I will just say the Precambrian, the sequence stratigraphy is based on two things. One is net sedimentation, and another is your sea level change. And because of microbiota cover during the Precambrian, net sedimentation rate is much higher. That's why it is expected that during the Precambrian, the sequence stratigraphic element and the sequence stratigraphic element in the Phanerozoic could not be same. Okay, so I have worked many Precambrian sequence, and I noticed that HST means high-stand system trap, which is a common coarsening of parasequence. They are very common in the Precambrian, not the transgressive system trap. So this is, I'm concluding here. I'm already late, sorry. But if you have any question, you can ask me, particularly students.
Thank you, Shubhi. So this is a time for interaction. Just if you have any question, just you can ask.
Please.
This is not a question. I will just ask you to comment that can be a...
Mike, please. No one is there. Ask. He's coming. Tapon.
This is not a question. I just want your comment on this, that the Precambrian microbial mats are very well preserved in the Precambrian rocks, which is not there in the modern sediments, Phanerozoic sediments. So what do you think, which is more advantageous for sedimentologists? The Precambrian rocks, which has microbial mats and preservation of a different kind, or Phanerozoic rocks, which has vegetation, animal and sediment interaction, that is better for understanding the environment and climate and depositional features, so, which is more beneficial.
Yeah, it's both ways correct, Tapunda, because you see, Precambrian always give you the better primary structure as you are a man worked in both the environment. Bioturbation is a big problem in Phanerozoic. Bioturbation destroys the sediment primary structure and many things as well. Again, if it is metamorphosed, then problem. If it is structurally deformed, they will destroy many things. Even twofold or threefold deformation, you cannot measure the primary structure as well. Or you can utilize the paleo-directional thing. Okay, so these are the problems. But as you also worked on Precambrian for many days, and I think in Precambrian there are some advantage because preservation is very good, and particularly in our country, in India, the Proterozoic sediment preservation is so good. I am fortunate to see some good section in South Africa as well as China. but our preservation is excellent. So that is one advantage for me, but really it is any.
Is there a question?
Thank you, sir, for such an enlightening talk. Sir, I want to ask, how can I differentiate between palimpsest ripple and actual ripple?
And?
Actual ripple, when I see it in the
palimpsest ripple, if you see, there will be no, if you see the vertical section, you will not get any lamination. As in case of, there are a term in false ripple or false ripple, a term that in our earlier, nowadays this book is rare, Hills, there was a structural geology book, Hills, by Hills. There I have seen false ripple. So false ripple like this, you will not get any crossbedding. Okay? Easily you can identify.
Okay, sir, thank you.
Okay. So we just, it's not a question, just an opinion, that in one paper, Professor Zaleka, he wrote that for preservation of any laminations or bed or any bed form, algal mat is this. Otherwise, that will be destroyed. What's your
I cannot follow your question.
For preservation of any laminations or bed or any bed form, insects, algal mat is extremely best. Otherwise, that will be destroyed.
That is true for but in Phanerozoic sediment there is almost no algal mat or bacterial mat unless and until there are some.
It is there, but it is harder.
But not only difficult to get, metazoan pressure is so much, it's difficult to get unless and until it is extreme climate. As for example, if the salinity is very high, then you can expect. If the temperature is very high, you can expect. Otherwise, it's difficult to expect. You can get for a time being, maybe some restricted environment as a lucky situation in some swampy area in Chandipur, we observe this. But otherwise, difficult to get because of metazoan pressure.
But also it is.
Yeah.
Okay, thank you. No question. Thank you.
So thank you for your patient hearing.
So our next paper will be delivered by Alono Thodi from Nagaland University. The title of the paper is Implication of Soft Sediment Deformation Structures in the Neoproterozoic Simla and Jamsar groups, Himachal Pradesh, Lower Himalaya. Okay, this is there.
No pockets. Good afternoon, ladies and gentlemen. Firstly, I would like to thank Professor Subir Sarkar for delivering such a nice talk. And because I respect him as a teacher, I've never sat in his classroom as a student, but I grew up geologically, drawing so many inspirations from the plethora of works that he has done on microbial-induced sedimentary structures, which remains to be one of my core research interests till today. So, starting my presentation, I shall be delivering my talk on implications of soft sedimentary deformation structures
in the Neoproterozoic Shimla and Jonsar groups, Himachal Pradesh, Lesser Himalaya. So the objective of the presentation is to study the different soft sedimentary deformation structures that have been documented in the Shimla and Jonsar districts. Shimla and Jonsar groups. So the Shimla group and the Jonsar group are considered to be coeval, with the Jonsars deposited towards the hinterland and the Shimla group towards the seaward side of the basin. And both the basins lie unconformably over the Shali group, the Darla volcanics, and the Dioban group of rocks. And they are unconformably overlain by the Blaney Formation, the cryogenian Blaney Formation. Both the Shimla group and the Jonsar group are dominated by carbonates towards the bottom, and towards the upper part they are dominated by siliciclastics. So this is the map of the study area. It is in Himachal Pradesh, and the study areas have been highlighted there. This is the geological map of the Shimla group of rocks in Shimla and Solan district, and this is the study area in the Shimla group of rock. This is the geological map of the Jonsar group in the Sirmaur district, and this is where the soft sedimentary deformation structures were documented in Sirmaur district. So these are the different soft sediment deformation structures that were documented in the Shimla group as well as the Jonsar group. Now, what are soft sedimentary deformation structures? These are deformation structures which are formed in sedimentary rocks before they consolidated. So the first is convolute laminations, and here you can see that this is from the Shimla group, and these are the convolute laminations from the Jonsar group. You can see that all these laminations are crumpled in between, but they are bounded by undisturbed strata both below and above. These are slumps from the Shimla group, and from the Shimla group and the Jonsar group, you can see that there has been slumping that has occurred in the rocks. These are lode structures in the Shimla group. You can see the finger-like projections from the underlying sediments. Even here in the Jonsar group, you can see the lobe-like structures, the lode structures here, and then finger-like projections into the overlying bed. These are the flame structures. Then bowl and pillow structures. So here you can see that they are lobe-like structures within the sandstone beds, both in the Shimla and the Jonsar group. Then kink bands. So you can see that they have an angular hinge and almost straight limbs in both the examples from the Shimla and the Jonsar. Here also you can see the kink bands here. Then recumbent fold. So you can see that the fold are almost overturned, and the axis is almost horizontal. And one important thing about the SSDS is the presence of chaotic beds within undisturbed layers. So these two photographs are from the Shimla group. You can see that there are chaotic beds here in both these photographs, and they are sandwiched between undisturbed laminated siltstones. Here is also another example from the Shimla group, chaotic beds and undisturbed beds both below and above the disturbed beds. These are chaotic beds from the Jonsar group. You can see the chaotic bed running across, and it is also sandwiched between undisturbed laminated siltstones. So here also you can see examples of chaotic sediments here sandwiched between undisturbed beds. And this SSDs have not only been seen in the field, but microscopically it is also visible. So these are the photomicrographs of this SSDs bearing siltstones of Shimla group. So you can see that there is a deformation that took place, which is visible on a microscopic scale. You can see king bands in the second photograph here. And these are photomicrographs from the Johnser group. Here also you can see that there are convolute laminations and a lot of deformation has occurred microscopically as well. So to conclude, most of the sedimentary, soft sedimentary deformation structures that we have seen here have occurred because of sediment loading, reverse density gradient, slope gradient, or gravity related triggers, or tectonism or seismic related triggers. And the chaotic beds within undisturbed beds, they also are strong indicators of seismic triggers for the SSDs. Now, all these SSDs have not been caused by seismicity alone. They have both seismic as well as aseismic triggers. So one of the main causes for the aseismic triggers of this SSDs is because of the high sedimentary input and the humid paleoclimate that existed during the deposition of both the rock groups. Previous studies on the Shimla as well as the Johnsers have indicated that the basin was shallowing upward with with high sedimentary input into the basin. So probably this deformations occurred because of the increase in the sediment budget into the basin, and also the presence of abundant stromatolites and microbial induced sedimentary structures, and also the previous geochemical studies have indicated that the climatic conditions were warm and humid during the deposition of these two rock groups. And both in the Johnser group as well as the Shimla group, we find interbeds of volcanics interbedded with the Kunihar formation and the Chandpur formation, from which most of the sedimentary from where most of the SSDs were documented. So this is a direct indication that some of these SSDs may have had some seismic triggers. These are pillow basals from the Kunihar formation. You can see the pillow basals interbedded with lying on top of the laminated siltstones here. So the cause of the seismicity in both these two rock groups may have been related to the rifting of Rodinia supercontinent. Many studies recently have indicated that these two basins were deposited during the rifting of Rodinia supercontinent. So probably because of the rifting of this Rodinia supercontinent, there were volcanic activities taking place during the deposition of these two rock groups, which cause seismic triggers, which cause the disturbance or the deformations in both these two rock groups. These are the references that I followed. Thank you. I'm ready to take questions.
So, do you have any question? Dr. Dasgupta? You are walking there, so.
Dr. Thori,
yes.
Very glad to see many photographs from lesser northwestern Himalaya. Now, I think that is what I am thinking. I have not studied that area directly. Some of the structures could be secondary due to shearing. Some of the structures that you have shown because the impression of the asymmetric folds,
Okay.
They are very good proof of shearing.
Okay.
So some of the, okay, that point, I think.
Yes, sir. It may be possible because some sections are.
The king pens.
Yes, and then some of the in some cases we saw axial planar cleavage, static cleavage developing.
Okay.
Those are very much secondary structures.
Okay, okay. Yes, sir, that may be possible.
Okay. This point I would like.
Okay, thank you, sir. Thank you, sir. I'll keep that in mind.
Why are you relating this HPCT with the breakup of Rodinia in this case? What are the evidences? What are the independent evidences of the relationship of these deformation structures with the breaking up of Rodinia supercontinent?
Okay. So the underlying beds of the basement of the Shimla group is the Darla volcanics. So the emplacement of the Darla volcanics has been, like in so many recent papers, the emplacement of tholeiitic basalts and also this Darla volcanics have been correlated with the rifting of Rodinia supercontinent. So that's the main basis. And these volcanics have been documented. Some of these volcanics have been found interbedded with the Shimla group, the basement formation of the Shimla group. So it also indicates that the volcanism and sedimentation was taking place alongside.
So, I have one question.
Okay, sir.
You have shown so many structures.
Yes, sir.
But I think the best one is the convolutes. And you are fixing earthquake.
Yes,
the
sir.
triggering agent.
Sir, not only earthquakes, there are seismic triggers as well.
That is a relative tectonism.
Yes, sir.
That seismic shocks are generated from tectonic.
Yes, sir.
You know, there are at least 21 triggering agents which can produce these resistance.
Okay, sir.
Convolutes.
Yes, sir. Yes,
So
sir.
how you are negating all those processes, all those triggering agents? Only you are fixing the seismic.
Like I was saying, there has been volcanism involved along with the going on parallelly with the deposition. So yeah.
Instead, just you go through the details.
Okay, sir. Yes, sir. I'll do that. Yeah. Thank you.
It's a good work. Just you carry on.
Okay. Thank you, sir.
And you should mention the rock types. You know, I think it's a little bit better more. So what?
Yes, sir. They are meta sediments.
What Professor Ghosh was saying that some of the structures are really of secondary origin. It's a tectonic origin.
Yes, sir. Like the rocks from the lesser Himalayas. Yes, sir. Yes, sir. They are surely structural disturbances have taken place. Yes, sir.
Actually, the convolutes.
Okay.
They are definite associates.
Okay, sir.
Before fixing the triggering agent, you should negate all other possibilities.
Okay, sir. Okay, I'll keep that in mind. Okay.
Thank you.
Okay, thank you, sir. Okay, thank you, everyone.
Okay. The next paper will be delivered by Javed Iqbal. And he will be talking on morphotectonic analysis in part of Udaipur district, Rajasthan, using geomorphic indices.
Excuse me. The slides changes this one. Okay. Thank you. Good afternoon, everyone. I'm thankful to this organizing committee to give me this opportunity to present over here. My presentation is a morphotectonic analysis in part of the Udaipur district. Actually, the basis of this study is based on the Professor Wu et al. Has given the idea about this GPS measurement in 2007 to 2011 suggests that the Udaipur blocks is moving 49 millimeter per year towards the northeast direction. This is the intracontinental part, the Udaipur area, and the intercontinental deformations took place in Indian plate due to the collision between Indian and Eurasian plates. And the Roy and Jacker also said that this intracontinental deformation is responsible for the release of strain along the major faults. It is a stable cratons like Udaipur. Here the geomorphic indices has been used to understanding the landform response of active deformation process, and this is a reconnaissance tools to differentiate zones about the active tectonics. Mainly for the study of the morphotectonic analysis, the drainage pattern is very much influenced by this active tectonics. So we have analyzed the main river. The Ahar river is passing through this region here. Here the study area. This is the Ahar river passing through this region. So we have used the study the geomorphic indices of this Ahar river, and this is the Udaipur city lies here, and which is very much well-known tourism, and so and this tourism is also directly related to the economy. So for the development of this economy, we have to attract the tourist. So for the attraction of the tourist, we have to develop the cities also, and so we have to study the tectonic activity of the area, and here the morphotectonic analysis has been carried out. We have subwater 10 subwater set has been divided here for the study. This is the map. It is from extracted from GSI, and where there are two major belts. That was the Bhilwara belts and the Udaipur Jaral belts, which is lies in this Aravalli supergroup, and the Udaipur Jaral belts exposed as the inverted V-shaped area with the tapering end of Nathdwara. And northwest southwest trending this Udaipur, and this is the lineament of the Rakhavdel lineament, which is intersected between the older. These are the older and these are the younger sequence of the rocks, and these are the Udaipur Sandarbur, northwest southwest. These are the Udaipur Sandarbur lineaments. It is a contact between the Devari and Udaipur. These are the Devari and Udaipur group of the rocks. And the northeast southwest trending Chambal Jamnagar lineament, these are the lineaments which is cross-cutting the Rakabdev lineaments. And Darwal and Jogiewan lineament, this is the parallel lineaments which is contact between the Balicha formation and the Udaipur group. And lithologically, this area is mainly metavolcanics, conglomerates, dolomites, phyllites. These all the group are mainly chlorides, schist, chloride, schist, like these are the. And this region was active zone of sedimentation, distinct tectonism and repetitive magnetism during the end of the Mesozoic, according to Bakliwal and the Ramaswamy. And we have taken the methodology as the drainage network has been delineated by two methods. We have used a survey of India and also by the extracting from the SRTM dam. And the geomorphic indices of various geomorphic parameters like SL, stream length gradient index, valley flow width to valley height ratio, hypsometric integral, mounted from sinuosity, asymmetry factor, all such these has been computed. And then the relative index of tectonic activity has been computed using all these parameters. And then for cross-checking the stream deflection and lineament analysis also, and also the field evidence has been carried out. This is the stream length gradient index, where SL and these are the formula has been used, where the DH is the elevation differences of elevation between 2 points, and DL is the length of that stretches, and L is the total length of the stream. And we have found we have seen that if the SL value is more higher than the area is, we can say that the area is tectonically active. But in some cases, in the soft sediment, the SL value may be low when it is a strike slip fault happened there. And according to this scholar, SL value has been classified into 3 classes. In these classes, our study area, all the subwater set has fallen into class 3, whereas if we have classified in this relative classification, then we have classified SL value up more than 200 and 200, 200 and 100. In this relative value, this area is tectonically more active as compared to the other. In some cases, whatever the average SL value is less, but in some places like these are the subwatershed 1, 2, 3, 4, and this particularly area where the SL value is more. Here we have said this is the river profile and the SL value. This shows that it is more than thousands of the SL value, which is, and then ratio of the valley flow width to valley height ratio, it is also indicating factor for the tectonic activity. Here it has also classified as the 3 classes, VF less than 0.5, 0.5 to 1 and greater than 1. If the VF value is greater than 1, then it is tectonically less active, and this area in comparison average value of the whole area, it is fall in the class 3, but in the some places where the river is crossing the fault zone, it is also very less value. We have calculated hypsometric curve and hypsometric integral. Here the hypsometric integral is if it is greater than 0.5, then it is convex hypsometric curve convex upward, and if it is 0.4 to 5, it is concavo convex, and this one is if the value is more than the 0.55, and if it is concavo convex hypsometric integral, then it is value is 0.4 to 0.5, and if it is less than 0.4, then it is a concavo convex. That is it is a youthful stage, it is a mature stage, and it is the old stage here. Here our area of subordination 2, 3, 4 are showing the class 2, which is a concavo convex, that is a mature stage, and in comparison to this in this area, this hypsometric, if we classify this based on the relativity, then this area is showing the more active as compared to the other. Mountain front sinuosity here, these are the mountain front. Here mainly the 800 meters of the elevations has been considered as a mountain front, and the gap of this elevation of the highest and the base is about the 300 meters. Here the mountain front in this zone, it is about class subwater set 2 is showing in one mount. There are two mountain front, where the one mountain front showing the 1.08, and the LMF is the length of the mountain front along the pediment or along the foothills, and the LS is the straight line of the mountain front. By this calculation, we have got this data, and although these in the average values, we have got the class 2 of the, that is the relatively this area is tectonically more active as compared to the others, in where the in particularly few of these mountain front are very much straight front has been found here. Asymmetry factor is also indicating factor for the relative active. Here the asymmetric factor, we have used the AR, that is the right sides of the area of the basins from when we see to the downstream of this area. And from here to here downstream, these are the right side and divided by the whole area. Here by this asymmetry factor, if the asymmetry factor is more or less than 50, in average, many researchers has shown that this is the average value of 45 to 55. If this if this value of 45 to 55, it is said that it is a symmetric basin or tectonically less active, and if the values below 45 and more than 55, then it is considered as the tectonically active. Here we have classified 3 classes. If is less than 35 or more than 65 is class 1, 57 to 65, and between 35 to 43 is class 2, and remaining this 43 to 57 is class 3. Here we have find out that the area is class 2 and class 3 has fallen here, and the direction is also shown at the tilting of this subwater sheet. Basin shape is also indicated here, and this by the basin shape here we have found that the watershed 2, 4 and 9 are showing these are showing the elongated basins, which is more young in nature. TTSF value is also indicating factor. This TTSA value is means that the reverse is how much deflected from the midline of the river, or midline of the basins, and this value is fall from 0 to 1, and if it is 0, okay. Okay, then here it is found that this area is more as compared to the others. Relative active tectonics, all these parameters have been compared here, and all these value, and we have classified into 4 classes. In this here this area is tectonically moderate active as compared to this area. The stream deflections, some evidences have shows that the highly streams has been deflected in highly about 67.7 degree, 85 degree, and and the lineament density, we have extracted the lineament from the filtered like Laplacian, Sobel's, and so all this method, and this shows that the western part of this area is highly dense lineament, and these lineaments are north-south trending, followed by this northwest southeast and northeast southwest. Some Bakliwal and Ramaswamy said, and some scholars says that these lineaments directions are younger in nature. And some field evidences, these are the major cracks found in the field, and this is the northwest southeast trending, and these cracks in zoom in position, we have seen that there are no vegetation in this here. Okay, these are the some field evidences where we have found this is the tectonic activity. Then this shows that the northwestern part of the mainly 30% of the area is tectonically active as compared to the other part. Thank you.
Yes. Any question, please? Okay. Thank you.
Okay, sir. Thank you.
Next speaker is Geologicalinstitute. Geologicalinstitute Chetia. Diagenetic response to tectonic stresses and deformation in the zeolic sediments of northeastern Himalayas, foreland basin, India.
Okay.
Good afternoon, everyone. Here is my presentation. My topic is diagenetic response to the tectonic stress and deformation in the zeolic sediments of northeastern Himalayas foreland basin, India. The zeolic sandstones of northeastern Himalayas in India hold critical significance for reconstructing the geological history and evolutionary dynamics of Himalayan foreland basin. These sandstones are widely studied for their sedimentological and diagenetic attributes to investigate the paleontological conditions, sediment provenance, and basin evolutions. This research investigates the diagenetic evolution of zeolic sandstone in the northeastern Himalayas and employing the optical microscopy and scanning electron microscopy to study the interreaction between the diagenesis process and the tectonic influence. Here is the study area. I have selected the study area of Ziadol River section that is belong to Arunachal and Assam border. tectonic setting and regional geology of the area. The Himalayan frontal thrust serves as the boundary separating the Shivalik sequence from the Brahmaputra alluvium, while the main boundary thrust distinguishes the Shivalik sequence from the lesser Himalayan sequence. Here, this is the Himalayan frontal thrust, and which is separating the whole Shivalik. This portion is the Shivalik sequence, and the Shivalik sequence that is separated from the Brahmaputra alluvium through this Himalayan frontal thrust, and the main boundary thrust that is here, and this is separated the lesser Himalayans from the Shivalik sequence. Karunakaran and Rao divided the Shivalik groups into three formations, that is Dofla formation, Subansi formation, and Kimin formations. Here, the stratigraphic successions of the tertiary sediments that provided by K. Sarai in 2010, but my study area belongs to the Shivalik group, that is here the Dofla formation, which is mainly dominance of micaceous sandstone with calcareous congregations, and Subansi formation that is the highlighted by the salt and peppery texture of the sandstones, and the Kimin formation that is the boulder bed. At last, after the Karunakaran Rao that has divided the Shivalik group, which is further correlated with Surma formation, Tipam formation, Namsang formation, Dim formation, and found in the Brahmaputra Valley by Dr. N. Singh in 1980. Petrography, while we are in a thin section analysis, we grouped the mineral constituents into four groups, that is primary, miscellaneous, lithic grains, and matrix cements. Quartz is the main dominant framework mineral that present in those thin sections. Here, quartz are divided. Different types of quartz are observed, that is unit, wavy, composite, pressure, and schistose quartz. Here, some pictures, some micro photographs that showing that under polarized light and under cross nickels, as the unit undulates of quartz are shown, pressure quartz are shown. Primary constitutes primary minerals, that another is feldspar, which is the second most abundant. And those feldspars are alkali feldspars and plesioklase feldspars. Alkali feldspars that are orthoclase and microcline. Orthoclase are identified based on Carlsberg twinning, and microcline that are on the basis of Creutzfeldt twinning. And plesioklase feldspar are identified on the basis of polysynthetic twinning. Then the miscellaneous as minerals that are accessory minerals which are present, and such as biotite, muscovite, olivine, pyroxene, and the lithic fragments that are the rock fragments of igneous, metamorphic, and sedimentary rock. Volcanic rock fragments, slate, phyllite, schist, and quartzite are the common rock fragments that are observed in those sandstone slides. And here the matrix minerals that are included are clay minerals like elite, carolinite, chlorite, and fine-grained mica feldspar, which fill the interstitial pore spaces of those slides. Here is the diagenetic response to tectonic stress. Yes, when we talk about the diagenesis, then we have to talk about the cementation and compaction. Cementation and of those sediments, those sandstones, the prevalence of silica cement highlights the influence of intense compaction and flow of the silica fluids and during the diagenesis. Another key features that are tectonic with a response to tectonic and pressure situations. The key features that are studied here are king mica bending, calcite replaced by silica, quartz overgrowth, transformation of quartz grain into chert, pressure solutions, grain to grain boundary of the grains, and the fractured grains. Here we are discuss about the king mica bending, and then those king mica bend that are present in the microphotographs, which are taken in under cross nickels or polarizing microscope, and the other image that are taken at the scanning electron microscope, that is back scattering image. This mica, king of mica bending flakes, is the common indication of mechanical compaction. Here, calcite is replaced by in the photograph, calcite is replaced by silica, which is this alteration is driven by the acidic dissolution chemical environment that typically occurs in the regions with the active tectonic processes. Then we ever talk about the quartz overgrowth. That is the overgrowth picture here for microphotographs that is taken under the SEM, and that's here the quartz overgrowth photographs are taken. But I want to inform everyone that the Shivalik sediments of northeast India, that is belong to the Arunachal, where the overgrowth of grain is not so common. It is very common in the northern, western northern part of the India. But little bit amount of quartz overgrowth are present, that is in the Dofla sections, Dofla formations. This process is likely closely linked to the tectonic activity, particularly in the regions undergoing the subsidence or burial. Then another is transformation of quartz grains into chert. Silica dissolves in the pore waters and reprecipitates and gradually replacing the quartz grains, and dead quartz grains are forming the chert. Here is the pressure solution as described. Engler and Masser, 1985, is a rock-water interaction process that leads to the forming of cleavage without involving the yield strength. This process, here is the photograph, has shown a silica precipitation along the grain boundary, which is describing about the pressure solution. Here, between the mica band, silica grains are present, and there is indicating a preferred orientation of the quartz grain that are within the mica band, which indicates about the tectonic effects and grain to grain interaction. Here in the photograph, the parallel grain to grain boundary are shown here, which signify that the long and straight grain boundary always indicates about the intermediate diagenesis according to Peterson. And then the fractured quartz grain are observed, which indicates the tectonic and the compressional stress of the area. The presence of these fractures as undulating axis of mica bands, clay minerals, and the lithic fragments undergoes the role of tectonic forces and the mechanical compaction in this diagenetic evolution of these sandstones. Now I would like to conclude my presentation on the key processes that are involved in these presentations. Cementation, that compaction, mineral replacement, quartz overgrowth, chert formation, and pressure solutions. These observations highlight the interplay of the diagenetic process and the tectonic forces, offering valuable insights into the regions of geological history and the basin evolution. Thank you. Here is my references.
Okay, we have time for a quick question, please. Okay, if not, maybe for the sake of running the review time, so we'll move ahead. Thank you again for your presentation.
Thank you, sir.
The next speaker is Dr. Nivedita Chakraborty. And she'll be speaking of the architecture and paleohydraulics of an early Triassic fluvial system, the Panchet Formation from Raniganj Basin.
Pointer and this changer, or I will make it here so that you don't have to turn around.
No, this is okay.
Okay, this is for changing and this is for...
Yeah, thank you. Respected Chairperson, my respected teachers and distinguished delegates from different institutions, my friends, dear research scholar and students. Today, my topic of discussion will be architecture and paleohydraulics of an early Triassic fluvial system, Panchet Formation, Raniganj Basin, Eastern India. Raniganj Basin is located in the heartland of Eastern Indian coalfield. In the year 2017, I started my fieldwork in Gondwana rocks of Raniganj Basin along with the undergraduate geology students of my previous institution, which is located at Mejia, Bankura. In the first couple of fieldworks, I visited only the Raniganj Formation. Then gradually, I took over interest on the early Triassic rock as well. And soon I had a strong feeling that there are significant changes in the sediment characters of these two formations. And then it was also that Raniganj Formation had much more attention, and the reason is quite obvious that it was one of the major coal producing horizon in Eastern India. In comparison, Panchet attention was less. In spite of some of the reputed journal published papers on granulometry, paleontology, there are some critical aspects in sedimentology that I thought need much more attention regarding the Panchet. And being a learner, today I would like to share some of my sedimentological understanding on Panchet Formation. In this work, I was accompanied by Dr. Anudev Mondol of this department and Ms. Lovely Burman. So quickly look back at the early Triassic time. It was initiated by with the largest mass extinction in the Earth history, worldwide fall in sea level, volcanic eruption, existence of Paleotethys at that time, widespread ocean anoxia, transition from late Paleozoic ice house to the later Mesozoic greenhouse, one of the warmest period in Earth history with no polar ice caps, very dry climate and wide subtropical dry desert belts. These are the highlights of my presentation. Raniganj Basin, as I already mentioned, that it is one of the major coal producing basin and east-west elongated fault controlled half-graben type intracratonic basin, covers an area of around 3,000 kilometers and accumulate around 22,000 thick continuous succession of Gondwana supergroup. Here is the location of Raniganj Basin, and this is the stratigraphic succession of the basin. This is the geological map of Raniganj Basin. Our study has been carried out in some tributaries of river Damodar, namely Bashpetali and Tetul Rock. And we did study the depositional scenario, fluvial architecture and the paleohydrological analysis. These are the panoramic view of the two sections. And I would like to quickly focus on the broad characteristics of these two formations. First, Raniganj Formation of late Permian age, broad shallow channel bodies, presence of bank attached bar and point bars, frequent association of floodplain deposit, profusion of coal, dark colored shale rich in carbonaceous matters and weathered sandstone which is kaolinized. On the contrary, Panchet formation of late early Triassic age above the PT boundary shows thick multi-storied sandy channel units, dominance of mid-channel bars, evidence of aeolian deposits, restricted occurrence of overbank finds, absence of carbonaceous content, dearth of coal, fresh unaltered feldspar, and remarkable presence of thin sedimentary deformation at certain stratigraphic horizons. Here is the facies disposition with paleocurrent direction. Above the PT boundary, so far we have identified 4 channel belts, and the facies characters shows that the grain size from pebbly sandstone to mudstone with the predominance of sandstone, and a remarkable horizon of thin sedimentary deformation structure below and above paleocurrent direction deviated, and also some of the character in the fluvial parameters. Now, what was the need of fluvial architectural element analysis? There are facies analysis, but still it is needed because fluvial environment itself includes a vast paleogeography. So similar kind of fluvial succession is expected in each fluvial style. Facies sequences thus cannot be considered as diagnostic for a particular river style. To overcome this kind of limitation, actually attention shifted to large scale sedimentary structures leading to architectural element analysis. For our present study, we considered nature of the bounding surface, external and internal geometry, primary sedimentary structures, spatio-temporal arrangement of the lithofacies, and paleoflow direction. Now I would like to mention the element one by one. The channel element, which is the most dominant and largest identifiable autocyclic element. Scale and shape is highly variable, sculpted by concave of erosional base. Primary sedimentary structures are mostly traction current generated, unidirectional paleocurrent. 2 types of channel pattern we observed. One is deeper and narrower, and other is the shallower and wider. Both are internally trough cross stratified. Next, down current accretion element attached with the mid channel longitudinal bar, internally compound cross stratified, where the largest and the smallest forces both are oriented to the regional flow direction. And transverse bar element, which is attached to the mid channel transverse bar. It shows tabular body geometry, internally tabular cross stratified. Here also forces are oriented to the regional flow direction. Now comes to the laminated sand sheet element associated with overbank finds. Laminated sand still occurs like thin blanket lenticular body commonly associated with crevasses channel within the floodplain, and overbank finds are basically the finest fractions in the floodplains. It's very limited in occurrence in case of Panchet in comparison to Raniganj, and they commonly occurs along with the channel fields and crevasses channel. We also observe some aeolian deposits mostly associated with the transverse and longitudinal bars. They are internally translatin stratified, alternate darker and lighter laminae are present. There are some adhesion ripple associated also. Here we have tried to show the distribution of different architectural elements within different channel belt. This is for the channel belt 1 at location 1. From 1 to 6, we have showed that different lithofacies, and we have tried to connect them with the architectural element. And we repeated the same exercise for the channel belt 2 and channel belt 3 for the L3 locations. Here the significant part is a presence of a thin sedimentary deformation layer in between CB2 and CB3. Now comes to the second part of my presentation, which is paleohydrology, which is basically study of the fluvial processes and their hydrological implication. These are the most popular the parameters which are dealt in paleohydrological analysis. When we plotted the parameters for all the 4 channel belts, it has been noticed that the common declining pattern of the parameters was interrupted in case of channel belt 3. Please keep in mind that the SSD horizon is present above this CB2. In case of slope, the trend is just reverse, that is, slope is lesser in CB3 in comparison to CB2. Possibly, this is the reason behind the shallower and wider channels that we obtained above the SSD horizons. Here we have tried to place all the significant parameters in a common histogram, keeping Raniganj formation in the left. We also checked the ephemerality index, which is basically the difference between bankful discharge and mean discharge divided by drainage area in square kilometer, but this is the numerical relation, which is ephemerality is basically the river which does not have water during all the season. It's not perennial in nature. When we checked it for the latest Permian and earliest Triassic, we found that it is quite high. So it indicates a dry and arid climatic condition for this latest Permian to early Triassic interval. Now, if I like to summarize my presentation, then I would like to mention that a worldwide fall in sea level during the early Triassic time probably had a significant effect on landscape and climate, at least during the initial phase of Panchet sedimentation. Panchet channels were morphologically multi-storied, deep, narrow or shallow wide. Overwhelming finds are limited in occurrences. Channel fields and bar elements are often interbedded with aeolian deposit, indicating warm and aridity in climate. However, presence of adhesion ripple indicate intermittent damp conditions. Architecture and paleohydraulics of Panchet fluvial indicates an overall low sinuosity, energetic, sandy, ephemeral, braided river system in comparison to Raniganj, which is basically a high sinuosity meandering system as per our observation in our field work. High rate of bedload transport due to rifting prevailed in peninsular India during the Permo-Triassic time, possibly which catalyzed the braiding of rivers in the early Triassic times. An increase in different fluvial parameters except slope was noticed beyond a stratigraphic level, which is carved by remarkable presence of syn sedimentary deformation structures. Shallow and wider channels above the SIST horizon that corroborates this interpretation. Early Triassic Gondwana rocks possibly experienced a fresh episode of tectonic uplift and readjustment of paleoslope during the onset of upper Gondwana sedimentation. That's all about my topic. Thank you for keeping patience, and I acknowledge Professor Shubhi Sarkar for his constant support during this work. Thank you.
Thank you, Dr. Volpi. We have time for questions.
Dr. Chakraborty, will you please elaborate a little bit on two types of bar that you have recognized, longitudinal and transverse. How do you recognize and differentiate between them?
So the first one, this is the mid-channel longitudinal bar, which is internally characterized by compound cross-stratification, meaning two kind of forces. One is larger ones, and in between them there are smaller forces. These I have identified as the mid-channel longitudinal bar, and this one is the transverse bar, which is internally characterized by tabular cross-stratification.
What is the difference between the two, transverse and longitudinal bar?
Yes.
What is the difference between the two? How do you recognize them as transverse and longitudinal? You say something is transverse, isn't it longitudinal?
Sir, actually longitudinal bar occurs along the flow direction. If we see morphologically.
River or the bank of the river, is it a bank attached bar?
No, these are not bank attached bars, sir. Bank attached bar and point bars are commonly visible in Raniganj formation, which is not common in Panchet.
So what is the difference between the longitudinal bar in Panchet and a transverse bar in Panchet? What is a transverse bar?
So transverse bar actually occurs within in the channel part, but at an angle to the bank. and longitudinal bars are parallel to the bank.
How do you know what is the orientation of local bank?
Sir, for the association and the tabular cross stratification and in kind of the compound cross stratification when the forces.
Nowhere I have seen such classification of transverse and longitudinal bar in the geological literature. You have done architectural element analysis.
Yes, sir.
How do you recognize the transverse and longitudinal position of the bars with respect of the palliation? This is not clear in your presentation.
Okay, sir, I will keep in mind and we'll try to more.
Particularly in case of
Why don't you consider the channel direction? Channel flow direction, main channel flow direction,
sir,
and the orientation of these bars.
In both the cases, the forces are in the common, in the same direction of the channel flow, sir.
But
not alike the bank. In case of bank attached bar, it is high angle to the channel flow. But in this case, in both cases, they should be.
In case of transverse bar, it is likely that there should be some angular relation between the main channel direction and the bar. I think.
Okay, sir.
Okay.
Next one.
Hello. Do we have time for a small question? Yes.
I'm asking one question.
Okay, so you say that layer of deformed crossbeds or deformed sedimentary features are there. Now, some authors, they say that it's seismic in origin, earthquake related. What is your take on that? Do you have anything to say on that?
Sir, actually, we are doing on that part. For this presentation, I have not incorporated that. Miss Lovely Burman have made a poster on this topic. But so far, we have traversed a long area across the basin and we have observed this kind of sedimentary deformed layer in a persistent way.
Yeah, I know.
Yes, yes, sir. And that is also reported. We are trying to separate out the mechanisms and we have a reservation that it may be seismic, but we have to do more work on that, sir.
Okay, please do that.
Yes, yes, sir. We are trying. Sir.
And last thing is, you said there is a shift in the tectonic regime in the early part of the Triassic. Now,
that actually, sir, I observed in some literature, good reputed literature. I have not referred that, but.
Yeah, but if you can find out some evidences of that.
Yes, sir.
So I would be personally very grateful to you.
Thank you.
And thank you very much for concentrating sedimentologically on Panche.
Yes, sir.
I've been roaming around there for the last 35 years, but on paleontology I have mostly concentrated.
I have seen your paper, sir. I have seen your last.
No, that's not important, but it's very good that some sedimentologists are working on that. Thank you.
Thank you, sir. Thank you for the suggestion.
So, this was the last question.
Yes, sir. Yes, sir, of course. This one, sir?
The planar. These are planar regulations. Planar means sand.
Yes, sir.
But is there any marked interface in between two sand laminations? Marked laminations is there? Because this is very much prominent, you know?
This one, sir.
Region, foul region, like that. So what is the significance of this type of laminations?
Sir, actually we noticed some kind of aeolian signature. If these deposits were closely associated with some longitudinal bar and transverse bar, we were repeatedly observed. Yes, within the top part of the bar actually, sir. Towards the top of the longitudinal bar,
Do you think that this type of laminations is formed at higher current strength? It is only sand.
Sir, it may be Aeolian dune.
This is straddle bundles. It is pure sand with other laminations. Then.
But there is no mud, sir. No. In this case, there is no mud.
There is mud.
No.
So it is sand.
Yes.
Planolaminic sand.
Yes.
So we should expect this type of sediments at this place within the channel with higher current strength, not at the top of the bar.
Sir, but this may be translated strata or kind of.
Yes.
Okay, sir. I get.
Thank you.
Thank you, sir.
Okay, so we'll move on to the next presentation by Professor Parthasarathi Ghosh from ISI Kolkata. Who'll be speaking on a graph-based study of dynamics of the Koshi River.
Good. Should I start? With regards to Professor Shah, I first thank the organizers of this seminar for giving this opportunity to address here to this August gathering. And thanks to the chairpersons. Today I'm going to talk about Koshi megafan, the evolution of this feature and the relationship with the changing course of the Koshi River, and how graph theory can help us better understand the dynamics of this system. So this is the Himalayan folded basin, and Ganga here is the axial stream, and Koshi is the easternmost major north bank tributary of Ganga. Koshi originates deep inside the Himalayan mountain belt, and it has a huge catchment there which receives an enormous amount of precipitation during the monsoon, mainly in the form of rain, and also lots of sediments are generated here, and everything comes out through a very narrow gorge in the mountain front, which is known as the Barakhetra Gorge, and gets spread over this North Bihar plain. So though we call it a plain, actually back in 1960, Geddes, with the help of a very detailed topographic map, showed the presence of very large, very subdued, low relief alluvial landforms present in this region. And he suggested that they were constructed by the Himalayan rivers, and the cone that is associated with the Koshi River is known as the Koshi megafan. It is quite large in size, slightly convex up in transverse section, and dipping very gently towards south. Now this region is extremely flood prone, and it is well known for recurrent major floods, and these floods have been attributed to the changing course of the Koshi River. So back in 1966 and again in 1987, workers have tried to document the pattern of course change of this river, and according to this map, Koshi earlier used to flow through the eastern part of the megafan, then it gradually over the years it shifted towards west, and since 1949 it is flowing along the western margin of the fan. And why this is happening? It has been attributed to the fact that repeated nodal avulsions are taking place very close to the fan apex. What is the avulsion mechanism? If we just consider a very schematic version of the channel floodplain system here in a flow transverse view, then you will note that within the channel, the flow is much more perennial. It flows almost through the entire period of a year. And so the sedimentation is continuous there, but only during a flood, water level rises and water and some amount of sediment spills over to its adjacent floodplains. So that means that with time, the channel belt will aggregate faster compared to the floodplains. And if these things continues, channel will become super elevated and the whole system is going to be mechanically unstable. At some point of time, some part of the bank will fail, water will drain out through that gap and start flowing through a new downstream path, and the river will avulse. So this is the mechanism that was considered by Mackay and Bridge in 1995 for a numerical simulation where they could successfully recreate the east to westward shift of the Koshi River, and then they ran the simulation little further to suggest that in future the river is then again going to come step by step towards east. So all the questions were answered, everyone was happy, but then something happened. What happened? This satellite image taken on 8th of August, it shows that the Koshi is flowing through its usual course, western edge of the fan, and then on 18th of August, it breached its left bank embankment and started flowing directly to the axial part of the mega fan. It was not supposed to do that. It was supposed to come back step by step towards east, but it didn't do that. It jumped directly to the middle. It was a major disaster, 15-kilometer wide sheet of water flowing. It was inundation persisted for the next 2 months. It caused incalculable loss to life and livestock, livelihood. So after the flood, people started looking at the satellite images to see the new channel that has been formed due to this avulsion. So this is a pre-flood image. When you compare it with the post-flood image, okay, where is the new channel? There is nothing new in this, nothing much different in these two. The drainage pattern seems almost identical in these two images. So what is the channel? So further investigation suggested that megafan surface, if you look at the megafan surface, there is always a persistent drainage system present there across many flood events. Even the 2008 flood, major one, did not modify it significantly. Now, if you map it, you'll find it is something like a network, which is made up of channel segments joining and bifurcating. It's not a radial pattern here. So this pattern is suitable to be modeled by graph theory. So when you model it, it looks like this. And what is a graph? Graph is a mathematical model for describing the relationship among the objects. In their term, objects are called nodes, and nodes are attached with edges, like this one. So this graph, it is a directed acyclic planar graph. It has 16 entrances, 12 exits. They are leaf nodes. Leaf node means either they do not have an inbound edge or do not have an outbound edge. And compared to that, internal nodes are the nodes where you have at least one inbound edge and one outbound edge. So we have 16 entrances, 12 exits, and 205 internal nodes connected by 337 edges. Why directed? Because these are channel segments and water can flow only in one direction. Why acyclic? Because if you start from a node and travel through the network using its directional connectivity, then you will be never able to come back to the same one. no loops. And why planar? Because everything is happening on the surface of the mega fan, no flyovers, no underpass. That is why. So with this model, you can start to answer some of the scientific questions. Like if we ask, which part of this fan surface is more prone to the flood inundation? For that, you take one entrance and one exit. And then you can compute all the routes through the network that connect these 2 points. And similarly, you can compute all the paths for all pairs of entrances and exits. So obviously these paths will pass through some of the internal nodes. There will be a large number of paths passing through some of the nodes, and there will be some of the nodes which are visited by only a few paths. So some of the nodes are busy nodes. So in a way, they have the more probability of receiving floodwaters during a catastrophic event. And if you count the paths passing through each individual node and plot them in a map, you'll see that the busiest nodes are sitting directly on the top of the path that was taken by the 2008 floodwaters. So the structure and connectivity of the network does have a role to play in guiding the floodwaters. You can ask other questions also, like if you enter through an entrance, can you go to any of the exits? Is it possible to do that? The answer is no. If you enter through these entrances, you can reach only these exits. And for the eastern sector also, it is similar. But if you enter through one of these entrances, you can access a much larger area on the fan surface and come out through these exits. So, finally, conclusions are, the drainage network is not characterized by a radial arrangement of branches where individuals bifurcate downstream again and again like a DFS. It is a network of branching and rejoining channels. Floodwaters entering the network through one of the entrances can access only a part of the network. It is not possible to access the entire network simultaneously. The part of the network that will be inundated depends on the choice of the entrance. And finally, that would mean the observed shift of the Koshi River can also be perceived as various choices of flow routing through a pre-existing network of channel instead of creation of a new channel every time due to nodal aversions. If I have more time, you can do some more experiments with this type of, once you have this type of model, like you can ask the question, why we cannot reach all the exits if we enter through an entrance and travel to the network. Network spreads all over the surface. It is because of the certain property of the network, there are certain disconnected components in the network. That's why if you enter through the western gate, you go to the western exits only. So what happens if I have a this is because the graph, what we observe is not a fully connected one in a planar sense. So if we can experiment with a fully connected planar graph like this one, this is a synthetic one, and this was all the travel costs are computed based on local slopes. And if you develop some kind of graph traversal algorithm, then you get how to do it. Just a moment, sir. Okay, it's running. It's a simulation with a fully connected graph and with our graph traversal algorithm that we are experimenting with at this moment. So the problem, it is not a very good, results are not very promising because routing experiment gives you, with a fully connected one, gives you all the possible routes, but not only exclusively the route that was taken by the 2008 flood waters. So the discontinuities in the structure play a role in guiding the flood waters. Thank you very much, sir.
Thank you very much, Professor Ghosh. Maybe we can, as the next speaker gets ready, we can take a quick question.
Yes.
The next speaker is Dr. Rajarshi Bhattacharya. If you can come up to the stage and we can take a quick question for Professor Ghosh.
Partut is a very really exciting portrayal of the channel system and the result. So my question is, why this kind of disconnected network has been produced? Is there any reason for that? Is it always this kind of disconnected network of channels that characterize the megafans, or it is particular for Koshi, or is there any reason for that? I understand that the disconnected network of channels was the reason why it took a particular path. It cannot go anywhere or not even systematically shaped. But is there any reason why the graph pattern is so, why the channel pattern is disconnected on this Koshi megafan?
Very simple answer is I do not know. Actually, what you do with a graph is you model what you can observe, and you keep on giving hypotheses and doing experiments to see what matches, what gives your answer. But it is possibly related to how the flow is. You have a sheet-like flow when avulsion takes place. And it interacts with many topographic features and man-made features there. Those things are probably much more complicated things to answer for me right at this moment. I'm trying.
Thank you again, Professor Ghosh, for the presentation.
It's okay?
The next speaker is Rajarshi Banerjee from Presidency University, and he'll be speaking on characterization of correlative stratigraphic horizon within subaerial deposits of the upper member of the Bhuj Formation in the Kutch Basin.
A very good afternoon to everyone. I am Rajarshi Banerjee from Presidency University. The topic of my presentation is characterization of correlative stratigraphic horizon within subaerial deposits of the upper member of Bhuj Formation, Kutch, Gujarat. The Kutch Basin is a east-west oriented basin situated in the western continental margin of India. This is a lithological map of the Kutch mainland region where we have shown the 9 localities where we have carried out our fieldwork. This is a Mesozoic, the lithostratigraphic succession of the Mesozoic deposits of the Kutch mainland region. Our present study is concerned with the upper member of the Bhuj Formation. The upper member of the Bhuj Formation was deposited during the Albian age of early Cretaceous period in a dominantly subaerial environment. The stacked fluvial deposits can be subdivided into several channel fields and channel belts based on the order of the bounding surface. However, the correlation of strata in stacked fluvial channel deposits is very complex because the facies patterns of fluvial systems are laterally discontinuous over short distances and short time scales. Moreover, fluvial deposits lack prominent event horizons or marker beds and there is a scarcity of preserved index fossils. Therefore, our objective is to identify and characterize a laterally persistent horizon for basin-wide correlation of the fluvial deposits. This figure represents the stratigraphic log of the fluvial deposits in all the locations where we have studied. So we see that in most of the locations there are 5 channel belts from older to younger, and the top part of the 3rd channel belt in all the locations show modifications into either thick aeolian units or bioturbated units, which show extensive soft sediment deformations. The fluvial deposits were characterized by the different types of facies, which includes the trough cross-stratified channel sandstone, tabular cross-stratified sandstone, which have been interpreted as transverse mid-channel bars, compound cross strata interpreted as longitudinal mid-channel bars, and mudstone in flat plain overlain by planar laminated levee deposits. Moreover, the fluvial deposits show a lower dispersion in the paleocurrent, and in terms of petrography, the fluvial sandstones are generally poorly sorted. So as I mentioned earlier, that the top part of the 3rd channel belt show modifications, the fluvial deposits show modifications into bioturbated units. So in these 2 field photographs, we have shown that overbank deposits and abundant channel deposits being modified to thick bioturbated units. Also, as I mentioned earlier, that in the top part of the 3rd channel belt, the fluvial deposits show modifications to form aeolian deposits. The aeolian deposits can also be characterized by their common facies types, which include translatent strata, grain fall and grain flow laminae, and aerodynamic ripples. The aeolian deposits the aeolian sandstone is fine-grained and well sorted compared to the fluvial sandstone, and they show a wider dispersion in the paleocurrent pattern. So the top part of the 3rd channel belt, which has been modified into either aeolian or bioturbated units, show presence of soft sediment deformation persistently in all the locations where you have studied. The most commonly found soft sediment deformation types include convolute laminations, overstipend trough cross strata, slump folds, and sand dikes. The soft sediment deformation is not restricted to the aeolian deposits, but it is also found in the bioturbated units and the fluvial channel and floodplain. So as we see that the 3rd channel belt in the fluvial strata is different from the other channel belts. So we have constructed lithologs, stratigraphic logs for the 3rd channel belt in all the locations we have studied, where we have shown the modification of the fluvial deposits into aeolian and bioturbated horizons in layers. So from this log, we can make 3 observations. Firstly, the lithology of the SSD hosting sedimentary units is not uniform everywhere. Secondly, the thickness of soft sediment deformed horizon is not uniform everywhere. And third, the type and magnitude of soft sediment deformation also varies laterally across the different locations studied. So to explain the depositional setting, we have tried to show 4 different depositional models. In the first depositional model, we show that the initial channel belts, channel belt 1 and channel belt 2, being deposited by the Paleo River, where mostly trough cross-stratified sandstone, trough cross-stratified channel deposits and the different types of mid-channel and bank-attached bar formed, along with some floodplain deposits. After this, in the following this, in the second model, we have shown that the top part of the third channel belt began to dry up, and it got modified into aeolian deposits as well as bioturbated units. In the third model, we have shown that the top part of the third channel belt was affected by soft sediment deformation. Please note that the rate of sedimentation and thickness of unconsolidated sediments differ laterally across the basin. So therefore, the magnitudes and type of soft sediment deformation also vary in the different locations studied. And in the fourth model, we have shown that after the soft sediment deformation, the channel reappeared, and the fourth and fifth channel was deposited. The erosion, by eroding the top part of the soft sedimentary deformed layer in different magnitude across the basin. So to find the possible source of the soft sediment deformation, we tried to estimate the paleo slope. We tried to reconstruct the paleo slope of the river channel. So for this purpose, we measured trough cross-set thicknesses from the channel sandstone. Representative samples were collected from the different channel belts, from all the channel belts in the different locations, where we performed the grain size analysis and found the median grain size D50. So using the relations of Leclerc and Bridge and Bradley and Venditti, the dune height and the average bankful flow depth can be estimated from the trough cross-set thickness, because as shown in this diagram, when a sequence of dunes having non-uniform height migrate, trough cross-sets having variable distribution of thicknesses are formed, and the thickness of the trough cross-sets is directly proportional to the height of the bed forms. So using the estimated paleochannel flow depth, the median grain size and the median grain size, we estimated the paleo slope of the river channel. So we see that from the first to the third channel belt, the paleo slope shows a gradual decrease. But after the third channel belt, the paleo slope increases significantly. To summarize my presentation, firstly, the base of the soft sediment deformed unit is persistent laterally across all the locations studied in the basin, and so it can be considered as a correlative horizon. Secondly, the presence of laterally persistent soft sediment deformed layer indicates a major paleoseismic event. The increase in paleo slope of the river channel post the soft sediment deformation episode corroborates the former inference. And lastly, the nature, scale and lithology of the soft sediment deformed layer, soft sediment deformations may vary laterally in case of such tectonically deformed subaerial correlative surface. Thank you.
Thank you. We have time for one quick question, and request the next speaker to get ready. Next speaker is Shabushachi Mondo. In the meantime, we can take a quick question.
Hello. Hello. Show me the photographs, field photographs. Just one question. Go back. Further. Next. Next. Okay. Another one. Previous one. Just to show that truck cost irrigation is there. No. What's happening? Next. Go fast. No. No, just.
Oh, okay.
Next. Okay. The top right. You have mentioned that there is top classification in your lecture. But there is not top classification. It is planet level. The bounding surfaces are more or less parallel. And again, just there is variation of grain size across layers, coastal diffusion layers. So they may have a separate interpretation. And this SSDS, it represents a continuous phase of chalk, possible. So, and you use this SSDS for lateral code. So it has the strike processes. So, but you have to judge other criteria because that can develop by other triggering agent as well. Not only, but you said it's seismic.
Yes.
So there are other features because there are sand and shale. So you should get plain structures and other things that is fluidization features. Not there, only this type of complex convolutes are there. So keep it open, I think, better. It
Yes.
may not be of seismic origin.
Yes, sir, but the SSDs which you observed, they are persistent.
Yes, this is one side.
Yes.
And when defining causality
Yes.
and the internal structures, you should take care. And those aeolian, they should show grading of grain size. The core surgeon should occur with this of the causality core size. And they must show form discordance. If it is aeolian, you cannot expect flow of air in the same direction for a longer period of time. Days after days. No, it is not that. So it must show form discordance. The outer shell of the coastal layer and the inner coastal layers, they show difference in deep amount. Is that just? Okay.
Thank you, sir.
It was a nice presentation.
Thank you.
Thank you.
Okay, so the next presentation is by Ashok Prashad Mandal from BSIT Lucknow. Who will be talking about the origin of subsediment deformation structures, the Chorat sandstone in the Vindhyan Basin.
Good afternoon, everyone. So today I will be presenting about the origin of multiple subsediment deformation structures bed and multiple stair of progression sequence, its implication in interbasinal tectonics and storm pounding, in epoxy sediment dynamics and architecture. So before going to details on this topic, I will be discussing some introduction part about this topic. So before going to details, we have to know what is subsediment deformation structures basically. The subsediment deformation structures are specifically some deformation structures which form within the sedimentary rock during the sedimentation or soon after sedimentation, but it must be before the lithification process, and it's proceed by the liquefaction and the fluidization processes. But when we see some subsediment deformation structure are merely load cast and flame structures, convoluted lamination, ball pillow structures, and some other common structures is conduits, conglomerate brachia or fault folding structures. But question is how or what are the controlling factors controlled to form these subsediment deformation structures layer. So these subsediment deformation structures layers are mainly controlled by deformation mechanism, driving force and the triggering agent. So as we are seeing in this figure that a sand shell layer was alternating layer was depositing in its sedimentary depositional systems, and due to liquefaction and the fluidization process, initially the load cast structures has formed, And as this time going on and the liquefaction fluidization process continues, this load cast and flame structure continue to convolute lamination and followed by the ball pillow structure. And if further liquefaction fluidization process continue, it converted into the mud volcano or sand volcano structures. So we cannot infer from the substance different structures layer that how we only infer about the process, driving force and the deformation mechanism from the substance different structures layers. And there is no such substance different structures layers, and there is no such scale specification by which we can identify the triggering agent. And this triggering agent is broadly divided into two parts, mainly seismic and aseismic. Seismic means earthquake, and aseismic means specifically storm, wave action, tidal shear, slope break, and groundwater movement or bank collapse. As we are seeing in the background figure that this figure is taken in the Tista River. It was formed during the flooding event and followed by this bank collapse process. And on interest, so the question arises how we will be distinguished between the seismic and the aseismic process. Also on this process, in my PhD topic interest and my research interest, I have focused on the Vindhyan basins. This is the overall Vindhyan basin successions, and from my latest publication, we show that a substance different structure layer is present within a limestone depositions, and this substance different structures bed is continued over 57 kilometer stage at least. And beside this, the sedimentary facies has changed at onset of this deformation, and from this point we infer it that this is a seismicity event bed. But as we know, the Precambrian basin are mainly defined as the Epiric Sea, and Epiric Sea sedimentation is controlled by the interbasinal tectonics. And earlier studies shows that the thickness variation in the spatial variations and the substantive structures will be also continued in throughout the basin by the interbasinal tectonics. So here question arises in the Epiric Sea settings, which is defined by the interbasinal tectonic control. How will we distinguish the substance different structures layers if it's occur in the multiple layers? And this is the figure, entire deposition of the Vindhyan successions. And entire Vindhyan deposition is defined by into two parts, lower and the upper parts. And my present study is concentrated on the Chorat sandstone, which has a depositional range of 1.64 to 1.6, which is entirely deposited as the siliciclastic sediments from shale to sandstones. And it is defined bounded by the Koldar shale and Rampur shale, and earlier studies showed it was deposited in an high strength system track depositions. So on interest of this, we have studied the Chorat sandstone, and this the location one is specifically the present study area, where the other pinpoint place is very famous location in the Chorat sandstone, from where a number of publications has published in interest of the Precambrian lives and Precambrian lives. So, and when we have zoomed in the present study, we've seen that the Chorat sandstone, which is defined by these dotted white lines, have a three hillocks, and when we have traced it in the Gulat, we see that within these depositional settings there is three coarsening up packages, and each package has showing the thickness each package has thickness increasing, while thickness within in each sequence there are some multiple meter scale cycles. And as we are seeing in this figure, I have concentrated on this second coarsening up package, and this is the enlarged lithological log, and here we are seeing that each of the meter scale cycles is defined by a substance deformation structures layer, and this deformation structures layer laterally continue to the massive sandstone beds, which are associated with the slide plane and slump fault. The entire deposition sedimentary phases, we have identified entire sediment suction into three major phases association. One is mudstone, another is sandstone siltstone alteration, and the last one is specifically sandstone. This mudstone is basically defined by its finely laminated grey color shell with preservation of some lenticular bed geometry sandstone, and this lenticular bed geometry sandstone are specifically gutter cast and hammock with numbers of flute cast and shoal cast. And preservation of this mudstone inferring it was depositing in a low depositional settings, whereas preservation of gutter cast indicating storm pounding within the depositional settings, but absence of wave featuring indicating it was depositing within the storm depositional wave base. And when we move further in vertical succession, we observe that the sandstone shell into sandstone percentage have increased in the vertical variation, and the sandstone beds are mainly showing gutter cast, hammocky cross stratification, massive bed and ripple lamination. The preservation of the ripple lamination specifically indicating the depositional settings has entered within the wave depositional settings. And the last phases is mainly the sandstone phases, where the sandstone phases are defined by this tabular sandstone bed with very thin mud layer in between. And this sandstone beds has cross stratification, hammocky cross stratification and massive beds. And this entire depositional settings indicating it was also deposited in a high energy depositional settings with storm agitational settings. But when we correlating from the base to up at the top, it's defining it is a shallowing trend deposition. And as I have mentioned earlier, the subsediment deposition structures layers are mainly present at the bounding surface, and the subsediment deposition structures layers are mainly convoluted laminations. Here we are seeing this convoluted lamination, and other is the ball pillow structures. And these ball pillow structures are laterally transferred to the massive sandstone beds with slight plane association, and this is the enlarged view of the slide plane where we are seeing the silicon slide layers at the bedding surfaces. So the question arises whether this subsediment deposition structure layers is formed by the seismic and aseismic process. So to understand this, we have go through the deformation mechanism and the driving force, and as we all know, the subsediment deposition structures are layer formed by the liquefaction and the fluidization process. But as I have mentioned that subsediment structure layers are covered by the massive beds or hammocky cross stratification beds. So these two phases indicating there is a high rate of sedimentation, and because of this high rate of sedimentation, the liquefaction fluidization has processed, and due to this liquefaction fluidization, this deformation layer has formed. And storm domination indicating the driving force was mainly storm pounding, but its repetitive nature indicating there was some recurrent force which was forcing to occur this multiple subsediment deformation structures beds occurrence. So the most common recurrent events are mainly tidal shear or sedimentary overloading or seismicity event. But the absence of any tidal featuring discarding the tidal shearing process, whereas the subsediment deformation structures bed defining the bounding surface also discarding the sediment overloading processes. So here question arises the deformation must be formed by the storm pounding, seismicity or the interbasinal tectonics. But its repetitive natures and its shallowing trend indicating that this was formed by the interbasinal tectonics, whereas its lateral discontinuity to the undeformed bed also discarding the seismicity event. So as we are seeing in this figure that all of the subsediment deformation layers are bounding in each package, and each package are defining by the subsediment layers. So because of the interbasinal tectonics there are subsidence, and because of the subsidence energy has released within the basin, and because of this energy release the deformation has progressed over the kilometers. And because of this we are getting the bed within the depositional settings in a repetitive time nature, and this figure showing the three coarsening of parasequence are because of this large scale intrabasinal tectonics which are very common in the intracatonic rift. And because of this rifting settings we get the thickness variation in the lateral continuity. And from this study we infer it that within the intrabasinal settings along with the seismicity event, the intrabasinal tectonics and storm pounding has enough energy release by which we can get a number of subsediment structure beds within any sediment sequence, within any HST sediment sequences. So thank you. Thank you to all of the authors, and I am very much thankful to director of our institute. I am also very much thankful to chair professor and my teachers. Thank you everyone.
Thank you, Shobhita. Okay, I think for the sake of time we'll move on. Okay. So the next speaker is Dr. Anindya Mazumdar from NIO Goa.
One is here for Faraj.
পয়েন্টারই দাও এখানে লাগাই
This is for flight change and this is for pointing, the red one. Okay.
ঠিক আছে Yeah, thank you everyone, and thanks to the organizer for giving me the opportunity to give a presentation in such a prestigious platform and prestigious organization. This is slightly different from what you have been probably listening from the morning. This is more of ocean science and ocean sediments, and is a very special case of we are looking at molybdenum geochemistry in marine sulfidic sediments, a signature of methane pulses across the sediment water column. We are working on this program for quite some time now, and mostly in the Krishna Godavari basin, in the Mannar basin, in the Mahanadi basin, and in the Andaman basins. If you see that these are the regions in the Krishna Godavari basin and the Mannar basin where there are very active cold seeps. Cold seeps essentially means when there are a lot of methane from the deep sources come out across the sediment water interface into the water column. That process causes a lot of biogeochemical interesting things happens in the sediments. In the process, a lot of hydrogen sulfide is generated in the sediment. And these cold seep processes we see even in Cambrian sediments or even Cambrian rocks or even earlier rocks and sediments, we see the presence of these cold seep processes. So these kinds of regions have typically have a very high methane concentrations, high amount of hydrogen sulfide, methane hydrates are present, lots of orthogenic carbonates and bioharms, and all these things are present. And these are highly fractured controlled. That means there are deep-seated fractures in the sediments through which the deep methane comes up. What happens in the cold seep regions is, so these are the places which we discovered during 2018 to 2020. These are the active cold seep regions. You see, this is the bathymetry of the Krishna Godavari basin region, approximately in a depth of 900 meters to say 1200, 1300 meters depth. And these are the regions where a lot of you can say passive tectonics, that means shell tectonics, passive tectonics have caused a lot of deep-seated fractures and faults. And when we look at the image, when we try to image the water column, we see a lot of gases coming out from this region. A lot of gases, and these gases are methane gas, and which are as tall, the pillars of these gases are as tall as 700 meters. So you can see the huge amount of gas that is penetrating across the sediment water interface into the water column. Now, what is actually happening? In these regions where we find very shallow methane hydrate, which is a solid ice-like material, and a lot of methane coming out, and the sediment in these regions is absolutely black because the hydrogen sulfide concentration is extremely high. You can see the hydrogen sulfide concentration in millimolar going to as high as 20, 30, 40 millimolar, which is several order of magnitude more than the normal ambient seawater. Now this hydrogen sulfide, which is produced by a process, microbial driven process called anaerobic oxidation of methane, this hydrogen sulfide plays the key role in concentrating the molybdenum in the sediment water interface. And these are the structures which shows how the gases passes through or forms such kind of chimney-like structures in the sediment. And this shows the kind of chemosynthetic biomass, we call it chemosynthetic organisms, which are surviving on methane and hydrogen sulfide. These are called extreme life system. See, this amount of little bit of introduction is required before I actually move into the molybdenum system. And also we see such kind of strange organisms called tube worms. And just passing mention, these tube worm is one of the longest surviving organisms. When we found this tube worm, it was live, and its calculated age was around 125 years, and it is live. And it is surviving by eating hydrogen sulfide. It only survives on hydrogen sulfides, which is poison for all other benthic organisms. Okay. So we also find a lot of calcium carbonate in this region forming bioharms, but calcium carbonate is not the topic. So, and these are, you can see that the isotopic composition of this calcium carbonate is extremely negative, -45 to -50, extremely negative compared to the normal carbonate that we regularly come across from 0, -1, +1, and the calcium carbonates also look very different. So you can again look at this equation and see that so much of hydrogen sulfide is produced here. And this is typically the pyrites which are in the sediments. Now, if we see what this hydrogen sulfide is actually doing, so we tried to understand using hemogeochemistry, its concentrations and isotope ratios in the sediment core, that how these pulses of processes changed with time, pulses of the process, whether these events are episodic over time or they are continuous process. So MO is because this is the MO oxymolybdated form, and as sulfur is attached to it, more and more of sulfides, it forms a molybdenum thiomolybdated, and then they get concentrated in the sediment. Okay, and normally it forms such kind of clusters called iron MO thiomolybdated clusters, and we measure the delta 98 MO, which is the ratio of 98 and 95 MO, which using a multi-collector ICP-MS. We use NU3 plasma 3 multi-collector at National Institute of Oceanography. Okay, so what we actually did, there is a core collection, there is a pore fluid analysis, there is a solid phase analysis, all kind of parameters are measured to understand the basic biogeochemistry of the MO. I will not get into the details of this, but you can see we do a fluid measurements and the solid phase measurements of the core. Okay, when you look at the fluid measurements, it shows that presently the sulfate concentration from here goes down, and you can see the large hydrogen sulfide concentration here. Methane concentration is quite low at the top, and here it increases. And this is the process presently. Presently the sulfate methane transition zone is here, and main methane concentration in this region. But when we look at the core and we try to measure the molybdenum by aluminum ratio, we see there are so many regular peaks of MO relative to the background concentration of approximately 0.1 or 0.2. So many spikes, or you can say episodes of MO, and it becomes so high here. And these are the dates, these are the ages in kilo year, which is around 34 to 3.4 kilo year. During this time, there are so many spikes. Now each of this spike of high MO by aluminum is showing that these are the time when the MO was getting absorbed at the sediment water interface. Sediment water interface absorption is taking place. Yeah, so we also measured the carbon isotope ratio of the carbonate in the sediment, and you can see there's so much negative compared to normally what we see, say 0, ±1. The isotope ratios are very, very negative, and it's become more and more negative towards the top, showing that a lot of methane was coming up through the fractures, and they're getting oxidized to bicarbonate, thus precipitating calcium carbonate. And the process, as we have seen from the AOM process, it creates a lot of hydrogen sulfide, and those hydrogen sulfides were deposited in peaks. That means there are episodic bursts of hydrogen sulfide across the sediment water interface. But why episodic burst? Okay, so when we look at, again, when we measured the delta 98 MO, that is isotope ratio, we see that the isotope ratios are going very high here, episodically very high, and this is the seawater isotope ratio value of approximately 2.3. That means the MO, during each episodic blast of hydrogen sulfide and methane across the sedimentary interface, hydrogen sulfide was trapping the MO from the seawater, and so the isotope ratio is always moving towards the seawater, and the intensity is increasing as we move up. exactly what is shown by the sulfur isotope ratio and the carbonate carbon isotope ratio. Okay. So what is actually happening? This simple schematic diagram is telling us what is happening. When there are no fractures in the sediments, no gases, no methane gases and other things were allowed to pass through. But when there are a lot of fracture openings, gases try to come out. And when gases are coming out, as you saw in the previous equation, where anaerobic oxidation of methane is going on and it is combining with sulfate, microbiological reactions, they are producing the hydrogen sulfide. So whenever there is a stronger episodes of methane fluxes coming out through the fractures, deep methane is allowed to pass through, causing a lot of hydrogen sulfide increase. And so you create a episode of hydrogen sulfide enrichment at the sediment water interface, and so you allow the lot of MO to be trapped. This is exactly the time this is exactly the time where a lot of chemosynthetic chemosynthetic organisms also form. All those chemosynthetic organisms photographs that I showed at the beginning, they also are enriched during each of these episodes that we see in our sediment core. Okay, so we can look at this diagram. These are showing three different situations where we can see that the sulfate methane transition is here, a broad peak of hydrogen sulfide which is moving upward, sulfate concentration dropping. As the methane flux increases, you see the slope of methane flux is increasing, The sulfate methane transition zone is becoming shallower, even shallower here. What happens is that at this process the barium also dissolves, barium sulfate also dissolves, and the barium starts moving, causing a precipitation of barium sulfate at the top, and there is an MO enrichment. So there are three different situations which shows that how the increased flux of methane can cause MO enrichment in these regions. Okay. Now what we saw that there was an episodic rise of methane flux with fracture formation and episodic enhancement of hydrogen sulfide concentration at the sediment water interface. But when we look at the present day situation, we see that the methane concentration is much less and lower, and sulfate concentration is also lower at much lower depth. That simply means that after the precipitation of this part, the methane has gone down deeper into the sediment because of the closure of the fracture. Rapidly the methane has gone down. Interesting thing, when we look at the barium by aluminum ratio here, there are so many spikes, and all these spikes are actually telling us that as the sulfate methane transition zone was lowering, it is leaving what you call as barium fronts. Barium fronts means whenever there is a barium sulfate dissolution, barium moves up and precipitates. So when it going down, it leaves the barium fronts. So if the conclusion is that the enrichment of sediment H2S concentration at the sediment water interface via anaerobic oxidation of methane can potentially trap dissolved seawater in the form of certain complexes. Our study shows that MO enrichment in sediments is not a telltale signature of water column suboxyanoxia, which is a very normal concept that it tells about water column. No, it is not talking about water column, it is simply telling what is happening at the sediment water interface. It is possible to trace the past movement of methane by coupling MOFES and solid phase activities. And sulfide ratio also shows track the past sulfate methane transition zone. So MO enrichment above the present SMTs supports the upward movement of the methane, slow and rapid fall to the present depth. So this is what we see in this sediment core, and we see actually this all across the Krishna Godavari basin. We are all now seeing the same thing happening in the Mannar basin, Andaman basin, all those things wherever there is fracture control process. It may be a little bit different when you look at a purely diffusion control process, but these are advective processes. Thank you very much.
Thank you, Dr. Mathilda. We have time for maybe one quick question. Okay, that's good.
Thank you, Professor Madhukar, for an excellent talk. So my question is, the fractures that are important for this methane seepage, are those because of the overpressuring of methane or they related to some tectonic?
Yeah, these are related to the shell tectonics. Yeah, these regions have a slow creeping of the shells because of highly pressurized, you can say, shell layers deep, very deep in the sediments, a couple of kilometers deep. And also there is a high rate of sedimentation rate here. That has caused this shell tectonic process. And during shell tectonic, due to shell movement, lots of different folds and deep fractures form. And the gases always try to move through this. And when they move through, the methane moves through this. And then at the top, when they form within the stability zone, either they will form hydrate or the gases will start seeping out, causing the biogeochemical changes towards the top where sulfate is also entering into the system.
Thank you.
This is basically shell tectonics. Okay. Okay. Thank you.
Very nice work. And just wanted to know if you, in the solid phase, you have sulfates, obviously.
Yes.
How many species are there? Do you have the barite, calcite, and all the other sulfates?
Sulfates, we can see here barium sulfate.
Only.
Because the barium sulfate, other sulfates may be there, like sodium sulfate and other things, but they are the easily soluble salts. So barium sulfate is biogeochemically significant.
Okay. And what might be the source of the barium? What is there in the seawater?
Yes, normally most of the barium in the sediment comes along with the foraminifera that falls, because they have the microbarites, and then they get redissolved when there is a sulfate reduction. Barium sulfate redissolves and the barium starts moving up, and as it enters into saturation zone, it precipitates, forming a front.
Okay, thank you very much.
What question is? Your model is very much similar to Sedix-style sulfide formations, in a passive marine setting. So, and you're saying that the source of this fluid is from sediments.
Source of the methane.
Methane.
Yes.
So I think boron isotopes will give you some good result, whether that is deriving from sediments.
Because this methane isotope ratio is around, methane carbon isotope ratio is around -80. Anything around -80, -85, which is typically microbial methane. And they're coming from the deep microbial sources. At other places, we also see thermogenic methane. Like in Mannar, we see a mix of thermogenic and biogenic methane. But here it is all biogenic methane, which is formed in the sediments.
Have you analyzed those pyrite rhomboids?
What is it?
Pyrite rhomboids, those spherical.
Yes, yes.
Have you analyzed those sulfides?
Pyrite, we have measured the sulfur isotope ratio of this. They range from -40 to +10.
No, the chemistry of the rhomboids, they contain some other elements as well.
Yes, but that we have not studied. They will be containing certain other things, but we will need, those rhomboids will have, one of my student is right now is in Germany, and she is measuring the, using, I think, ion probe.
Just I am interested to know what are the lead zinc content in those.
I have not measured. Lead zinc content in the pyrites I have not
measured.
measured.
Is very much similar to Sedix-type deposits.
Okay.
Thank you very much.
Thank you, Dr. Vijay, one more time. And we now move to the last presentation of this session by Shreya Shengupta. And the topic is paleoclimate reconstruction and fire history in central Ganga basin using multiproxy lake sediment record.
A very good evening to all the respected professors, my dear colleagues, and my friends. The topic of my presentation is Paleoclimate Reconstruction and Fire History in Central Ganga Basin using Multi-Proxy Sediment Records. So before I start my presentation, I would like to say that India is a land of lakes, rivers and ponds and other various water features, and these provides hydrological budget to the country. It is important for agriculture, irrigation and as well as industries. So for research work, lakes can be used in various ways. So preliminarily, lakes can be used for paleoclimatic reconstruction, mainly to reconstruct monsoon variability. Other than that, lake sediments can be used for paleovegetational changes, which includes floral studies, land use, land pattern changes, changes in a catchment basin, and other than that, paleoecological changes, which include study of gastropods, ostracods, diatoms to see the biodiversity changes. And lastly but not the least, many anthropogenic activities or changes has been studied through lakes, especially pollution studies, water quality monitoring, etc. So for this, my topic deals with the paleoclimatic reconstruction, and my lake is on Central Ganga Basin. It receives about 85% rainfall from the Indian summer monsoon. So it is optimum for studying the ISM variability. The lake is located 28 km north of Lucknow city in Uttar Pradesh. It is known as Chandrika Devi Lake. It is located near the Gomti River Basin. The Gomti River Basin has three geomorphic features: the T2 or the regional upland surface, T1 or the river valley terrace, and T0 which is the active floodplain surface. And Gomti is a rainwater fed river, so there is no question of snow melt in the lake. These are the few abbreviations and formulas that I have used. Our research methodology includes sample collection using trenching method of 1.14 meter trench at an interval of 2 centimeter. The age depth model of the sediments has been measured using AMS radiocarbon dating and OSL dating. Grain size has been extracted, from which end member modeling has been done. Major and trace element ratios, TOC, 13C organic matter has been used, followed by pollen studies, and finally the biomarker or compound specific N-alkane studies has been done. Based on 3 radiocarbon and 2 OSL ages, we have constructed an age depth model, using our Bacon software. It gives a continuous age range from 75 Callier BP to about 5800 Callier BP. Now we have done the energy models, which are N members. Basically, we have confined the grain size into 4 major sedimentary processes: EM1, which is the low energy lacustrine process; EM2, which is the intermediate energy lacustrine process; EM3 is high energy fluvial lacustrine; and EM4 is the very high energy fluvial process. So other than that, we have the proxies that we have used are rubidium strontium, which is titanium aluminum, which is title proxies; phosphorus, which is used for understanding productivity; calcium oxide, zircon aluminium, which is used to understand the wind direction, wind patterns; FEMN, which is used to understand the axic and anoxic conditions in the lake; TOC and delta 13C. So in basis of which we have divided the lake into 3 phases. The phase 1, which is a fluvial phase, where we see more higher energy fluvial conditions are noted from 6000 to 5000 carrier BP. After 5000 there is a decrease in fluvial energy which is coincident with the increase in aridity in the central Ganga basin. But and this condition exists up to 4000 where we see that the EM4 decreases rapidly, and as well as 13C values shifts towards more C4 type vegetation. So we can say this is due to the influence of 4.2 kiloyear event, the lake has been formed, and from 4000 to 3000 this is a transition phase where open phased lake system is present. That means the lake is formed from the Gomti river, but it may have some connection with the Gomti river, and after 3000 years the complete closed phase system is noted. Closed phase lake system is noted where the proxies varies differently and more EM1 values are noted. Our data set is correlated with the other records of the Himalayas as well as the central Ganga basin, so which shows that it behaves similarly. Our record shows an anti-correlation with the Himalayan records. Then we have also used the biomarker studies. We have extracted lipids in straight chain L-alkanes from the sediments, and we have calculated the CPI, which is the carbon preferential index, average chain length, P aqueous, terrestrial aquatic ratio, delta 13C and TOC. We see that after 3000 carrier BP, there is a increase in CPI values, which indicates more terrestrial influences in the lake basin, which may be due to higher ISM conditions. If we have also done the stable isotope delta 13C and delta D values. The delta 13C values of the three dominant peaks are of C27, C29 and C31, and delta 13C values indicate thus whether it is a C3 vegetation or C4 type vegetation, while the delta D values gives us idea about the precipitation. From here we see that during the fluvial phases low CPI and more C3 or C4 type mix of C3 or C4 type vegetation is noted, while the delta D values remains towards more enriched. But after 4.2 event, during the transition phase, even though the values of C3 delta 13C doesn't vary significantly, but delta D values varies from minus 80 to minus 120, which is a very significant shift, and from which we also see during this time microcharcoals are present at very high numbers. This may be due to the burning effect in the lake, which may be caused due to human activity, or maybe due to the fire event caused after during the 4.2 event. In conclusion, I would like to say that our lake record shows a continuous record from 6,000 to 755 carrier BP, and the lake was initially a part of the fluvial system, but later on it became a lacustrine system after a 4.1 kiloyear BP due to a 4.2 kiloyear event and decrease in monsoon with increasing aridity. But after 3000 carrier BP, a continuous lake, a closed phase lake system was developed. But other than that, we also see some evidence of fire activity post 4000 carrier BP in our lake. These are my references. These are the acknowledgements and the institutes from which we have done the collaboration and publication. Thank you.
Thank you. We have a quick question for the speaker.
Yes, sir.
Can you clarify what are the main evidences of the fire events, different fire events, or maybe one major fire event that has taken place in one?
Sir, could you repeat the question?
What are the main evidences of fire events taking place?
There are two major events, the major evidences that we have noticed. One is the increase in microcharcoals. Is it not working? Increase in microcharcoals from 4.2 after 4,000 years, and there is a shift in delta D values from minus 60 to minus 120 or 120. But we have seen there is a paper in Sarangi et al. Which has shown that delta D values can be affected by climate change as well as fire events. If the sample is burnt, then the lipid is also burnt, and that is why it becomes more depleted. We have also done, which we have not shown, but we have done the modern plant delta D values, which is equivalent to about minus 200 and minus 180 parts per mil. This means that this modern vegetation also shows that it is more towards more negative, but this shift it is not well explained through literature. That means maybe due to the fire activity, as it is also corroborated by microcharcoals also.
How deep was your trenches from which you have collected sediment?
It is 1.14 meter deep. It is from a paleo channel in near the Lucknow city in Gomti River basin.
And what is the interval between each sample that you have?
2 centimeter samples. My sample resolution is like 2 centimeter, and the age there is like 100 years. No.
How do you collect the samples?
We have in the field we went and dug a pit up till the where we reach the water level, and then we from the bottom to the top we have measured 2 centimeter and we have collected the samples.
So the wall didn't collapse?
No, we had to ensure that the wall did not collapse.
Okay, thank you very much.
Thank you, sir.
Okay, thank you, Shreya. Thank the speaker one more time. And with that, we have come to the conclusion of the fourth session, and the final session rather, of this wonderfully organized conference. So thank you once again to all the 10 speakers for the beautiful presentations. And thanks to Professor Bhattacharya, the co-chair, and over to the organizers.
Professor Niranjan Dasgupta to come on dais. And also I request Professor Shubhish Sarkar, our keynote speaker, at the dais. Now, Professor Niranjan Dasgupta will felicitate our co-chair persons with a small memento. Okay, sorry. So, Professor Niranjan Dasgupta, sir, will felicitate our keynote speaker with a small memento. Professor Harendranath Bhattacharya will felicitate with small memento. Professor Ramananda Chakraborty will felicitate by Professor Niranjan Dasgupta. Now we would like to announce that we have a small tea bag and poster session is going on outside, and we will gather 6:30 for the validity sessions. In the meantime, we are distributing the certificates in the poster sessions for the respective participants.
Good evening, everybody. May I request all of you to please come within this auditorium, so we can start our valedictory session. Distinguished guests, esteemed faculty members and fellow participants, it's a privilege to address you all at this valedictory session of this 2-day-long national seminar. And on behalf of the organizing committee, I welcome you all in this valedictory session. Now, I request the 3 judges of this second day poster session to please come onto the dais. Professor Sujoy Ghosh, Dr. Probir Dasgupta and Professor Laboni Roy. I request you all to please come onto the dais. And I also request our joint conveners, Professor Gautam Ghosh and Professor Shankar Bose, to please come onto the dais. Now we request Professor Gautam Ghosh to felicitate our 3 judges for today's poster sessions with mementos, please. Professor Sujoy Ghosh. Dr. Probir Dasgupta. And Professor Laboni Roy. Thank you, sir. Now I request the judges on dais to please hand over the prizes to the winners of the first 2 days poster sessions. And there are 2 winners for each day. So for yesterday, the winners are Apurupa Banerjee from Shohid Matangini Hajra Government General Degree College for Women. So please come onto the dais. And Ahiri Kormakar from IIT Kharagpur. So please come onto the dais to collect your prizes. And the winners for 2 days poster sessions are Ammu JK from IISER Kolkata and Adrish Mahato from IIT Kharagpur. So please, both of you come to the dais and collect your prizes from our 3 judges. Yes, so from Professor Laboni Ray, Apurupa is collecting her prize. And Ahiri Kormakar, she will collect the prize from Dr. Probir Dasgupta, sir. And Ammu JK from IISER Kolkata, she will collect from prize from Professor Sujoy Ghosh. And Odrish Mahato is from Professor Laboni Ray. So thank you, sir and madam. Now I request few participants, whoever interested, to share their suggestions and views and their experiences for this 2-day-long national seminar. So anyone who can. So may I call Professor Shubir Sarkar? Is he present in this auditorium? Yes, sir. Sir, please, you can share your views.
Okay, thank you. So I'd like to convey my thanks to the organizer, especially to the master students, research scholar, and junior teachers, and of course my colleagues as well. But my special thanks goes to the juniors. They are so, the program has, though I was not present in the first day, sorry for that, and they organized it so efficiently and so just like a professional, some professional arranging this. So once again, I convey my thanks to all of you and of course the participant. Give a big hand to the organizer. Thank you.
Thank you, sir, for sharing your views and inspiring views. With this, I will request Dr. Sharifa Khatun, Organizing Secretary, to deliver the vote of thanks for this national seminar, please.
Thank you, Taposta. Good evening, everyone. As we conclude this remarkable national conference on dynamic processes of the earth, I have the honor of extending a heartfelt vote of thanks to all those who have made this journey a resounding success. This event has been a year-long journey filled with meticulous planning, dedication, and perseverance. And today, we celebrate a significant milestone in that journey. First and foremost, our deepest gratitude goes to our Honorable Vice Chancellor, the patron-in-chief of this seminar series, for his invaluable suggestions, constant availability, and unwavering support throughout this journey. His leadership and encouragement have been the guiding force behind this successful event. We extend our sincere thanks to the Director General of the Geological Survey of India for taking the time to be present at this conference despite his extremely busy schedule. His presence has added great value to this gathering. A special note of appreciation to the esteemed alumni of our department for their intellectual contributions, unwavering support, and generous financial assistance. Your involvement has strengthened the academic and professional foundation of this conference. We are immensely grateful to the Registrar for providing excellent support in handling the enormous administrative tasks required for this event. We extend our sincere thanks to the Finance Officer for his continuous support, and the Finance Department also deserve our heartfelt thanks for their efficiency and prompt assistance. Our sincere gratitude to the development officer for ensuring that all necessary infrastructural support was in place, making this event seamless and well organized. A huge thank to our departmental colleague for standing by us at every stage, offering every kind of support one can think of to successfully organize an event of this magnitude. Your cooperation has been invaluable. Also thankful to our office staff for their constant support. A profound vote of thanks to the family members of Professor A.K. Saha, as this seminar series is dedicated to his legacy. We are deeply grateful for your support, both in terms of invaluable suggestion and financial assistance. We extend our sincere thanks to all our major sponsors, Geological Survey of India, ONGC, Oxford Instruments, Brooker Invents, Geol India, and SBI. We also thank to other sponsors whose generous financial contribution made this event possible. Your support is truly appreciated. We also like to thank Dhar Brother as our printing partner. We want to give special thanks to our former HOD of the head of the department, Professor Arijit Ray, for his initiation to celebrate Professor A.K. Saha Birth Centenary Program. We are also thankful to our present head of the department, Professor Shankar Bose, for his constant guidance to make this event a great success. We are thankful to all the invited speakers from the different parts of India and the world for accepting our invitation and delivering their knowledgeable lectures. Also thankful to all the participants for your engagement, discussions, and sharing knowledge during these 2 enriching days. Your presence has made this conference a meaningful and memorable one. Now, I am requesting all the research scholars and students of our department to come on the stage. A very special appreciation of the student of the department, particularly our research scholar who willingly took charge and organized this entire event. If we, the faculty members, are the architects designing the blueprint of this conference, then you, the research scholars, are the skilled engineers and tireless workers who turned that blueprint into reality. Your commitment, enthusiasm, and resilience have been the driving force behind the flawless execution of this event. Without your dedication, this conference would have remained just a vision on paper. I requesting all the research scholars to come on the stage. And students also, please come. Bihari. I requesting all of you to give them a appreciation. With this, I conclude my vote of thanks, expressing my heartfelt appreciation to each and every one of you who contributed in making this event a grand success. Thank you all of you for your presence. There will be another lecture on the memory of Professor A.K. Saha on 25th May. In the month of May.